the stuff, but like don't stop swearing, I guess, or whatever.
Yeah, I'm gonna drop off. I will
gonna
see
mute
you guys on
myself.
live stream.
Great, good. Hello to everyone on the live stream early. How's it going? This part is going to be edited out when we post the final video, I hope. So this will go into the ether and no one will ever see what we say here. It's kind of an exciting liminal space, existing and not existing. It's kind of like when daylight savings time happens and like you do the same hour twice, you know? Then
Does
like,
that hour count?
What really happened during that hour?
I think you technically do whatever you want during that hour, right? Isn't that the policy?
Yeah, laws do not apply for the next 30 seconds of this live stream. All right, y'all, I like getting started on time. So let us jump right into session 3 of PLMW at PLDI 2020. I am super excited for this second day of stuff. This session is going to have 2 different talks in it, and I am very excited about both of them. Before we jump into the talks, however, I want to point out that we are again doing comments on questions rather on Slido. You can find the link if you are in the PLMW Slack there. If you are watching on YouTube, then it should be in the video description to the particular Slido thing for this particular session. I think there are no other logistics to be discussed here, so I am going to jump right into introducing our first speaker, who I'm super excited to welcome, Professor Michael Carvin from MIT. Mike has a lot of fancy awards. I was looking at his CV, and there are too many to possibly list here, but perhaps most notably he's a 2020 Sloan Fellow. That's fairly recent news from the last couple of months. However, I know Mike from the glory days of approximate computing several years ago, when both of us as grad students were working on programming languages to control and rein in the unruly nature of hardware that was allowed to give incorrect results. And Mike had a lot of amazing results in designing languages and tools and proof systems for making that kind of software more reliable. One thing I've been super impressed with in Mike's work recently is how he's also had tremendous impact in machine learning. Not that best papers are the indicator of all research success, but had a best paper at ICLR last year. And he's also been doing a bunch of, as you might expect, research that kind of combines machine learning and programming languages lately. But Mike is going to be talking more on the mentoring side of things. So please take it away, Mike.
All right. Yeah, thank you, Adrian. Thank you for that intro. And I'm happy to be here today to talk about research. It takes a village. So, before I get to that, before we dive into the talk, many of these PLMW mentoring talks, they'll have a warm-up slide, right, that just talks a bit about who I am, what I do, and other aspects of my life, which you can feel free to ask questions about, certainly during the QA or if something pops up during the talk. But so, as Adrian said, I'm Michael Carbon. I got my PhD from MIT and ECS in 2015. I then became a researcher at Microsoft Research for about 3 years, but I also concurrently started as a professor at MIT. There's a little bit of a space there, but concurrently really did happen there for quite a bit. And then as well, since 2015, I've had the fortune and privilege to be a dad and be a father to this, my beautiful little girl down here, Eliza. And it is entirely possible that you may see her bound through the room in this next hour. So if you see her, that's her. There's the evidence. So again, I'm at MIT. And as Adrian pointed out, I've done a lot of work in approximate computing. I think he did a great job describing that, as well as some of my more recent work where I've been taking that type of approximate computing mentality and started to think about it in the context of machine learning. So now back to research. So research, it takes a village. So the motivation for this talk is to talk a bit about, well, mentoring, right? This is the mentoring workshop, but I also want to talk about, the importance of mentoring and having a continued mentoring process. And the way that I have gotten to this talk is that I actually have an annual review that I do with graduate students in my group. And, if you're a young graduate student that's out there or undergraduate, I imagine this type of talk may make you anxious, right? But no, my students have actually, this is something that they've really enjoyed doing. Each year, where we sit down for an hour and a half or maybe longer and talk about a whole variety of different topics that I think are related to having success, success in academia, having a successful graduate experience. And so there are many different topics that we cover in this. And I have this whole form, this document that my students have to read, and then they're supposed to write their notes for themselves. And then we have this meeting. And so one topic is, of course, research, ideas. What do you enjoy about your research? What do you dislike about your research? What are new ideas that we're thinking about? What's not working? All these sorts of things. It then goes into professional development as well, where we think about, well, what about the process? These transferable skills that you're trying to build throughout this graduate process. So idea generation, communication, planning, coding, everything that's on there, right? What are your biggest improvements? What are the roadblocks? What are things that we can work on? And then we do another similar thing for the academic process, which I would say are these very, persnickety things that come about of dealing with just the filliness of academia. How do you get your papers published and going through that process? Now, one other thing that I have here as well is there's a section on advising and mentoring, and this is just an image from this document that I have there, and what it says is to effectively navigate the above areas. So what we just talked about in this previous slide, you need advisors or mentors. And so I asked, who have been your advisors and mentors in the year? What have been your successes? Where have you received good advice that is perhaps avoided some pitfalls? Where have you missed advice? Who have you been advising, just even thinking about practicing some of these mentoring skills as you're going through graduate school and growing into that type of responsibility? Now, so these are the questions, but if you follow this link that I have up there, it actually goes off to another document where I've written a bit more about mentoring. And this document lifts some core concepts actually from this document here. So down here, this link down here, the responsible conduct of research. It's this handbook. So responsible conduct of research mentoring. So it's this handbook here that's actually part of up on Columbia's website, where they have a wide variety of things here. But the way I ran across this was sometime during graduate school, if you get put on certain types of grants, such as an NSF grant, you actually get in this position where you have to go through some formal training about, what are research ethics and what are these things. And somewhere buried in one of those modules was one on mentoring. And it took me to this link. And it was very interesting because I at that time I was having, I was just running into the basic struggles of graduate school and trying to think about who I could lean on to try to move to this next or get advice on, to think about moving to the next stage of life. And I remember feeling this frustration, perhaps that, what do I look for in a mentor? Or who is my mentor? Is my advisor completely my mentor? And this actually had a lot of good things to say. So I'll summarize some of these. So one, what is a mentor? A mentor is someone who has experience with the challenges that trainees face, the ability to communicate that experience, and the willingness to do so. Right? So that is what they are, right? And in particular, a lot of people have this type of experience and will say all sorts of things, but a mentor in particular takes a special interest in helping another person develop into a successful professional, right? So I think that's where you go from senior sage to sense in the community and says lots of things at random to someone who's invested in you to seeing you be successful. Now, continuing on that, what does a mentor need to do? So this guide actually goes on and describes the truly complete mentor. It is a single individual who is able to serve as an advisor/guide, developer of talent, coach, opener of doors, advocate, role model, interpreter, organizational, professional, rules protector, rule setter, boss, right? And carries all of these functions on for a long-term basis, right? So I'm rushing through those because there's a lot that your mentor is supposed to contribute. And they even note it themselves. It says, this truly complete mentor is a rare species indeed. It's very hard for a single person to try to fulfill all these roles in your life. And so that leads to a question, right? And in particular, they clarify this a bit more where they say, not everyone embodies the characteristics needed in a good mentor. And it's important to note that thesis advisors and research supervisors are not necessarily mentors. And this clicked some light in my mind when I was in graduate school. So I had a fantastic advisor, thesis advisor, and still a great mentor me in many cases, but there's still things that I didn't think they had perhaps the right take on, or a take that I wanted to model and be able to use in my life. And this comment just opened the door to me, realizing that I needed more. I really did need more mentors, and that mentors could be everyone, as they point out, or could be anyone, right? It could be a faculty advisor, right? Another student, a faculty member, someone else, right? A friend, or just someone else with experience. And so the point of this talk, when I say research, it takes a village, is to note that there is, in science, we oftentimes celebrate the individual, right? So we put these contributions up there on a pedestal, and this individual on that pedestal with them, and say, this is this great theory that this person has contributed to the world. And it's very easy to take that mindset and think that this journey through graduate school, right, and this journey through life is this individual effort where you will be celebrated at the end. And we tend to not then think about this village, which are your peers, your mentors, your community, and how those people are so critical for getting to that success, that individual success or joint success, however you define that success. But these people are critical. And so the goal of this talk is to highlight some important research foundations where you need mentoring. I mean, the PLMW is a great venue because you get different perspectives on what's important, and all these things are valid. They should be included. But I also give you my particular take on things that I found valuable, things to keep alive in the way I think about research to become a broad-based, long-term researcher. And then I want to show you how I acquired these from my village, who helped me with these types of things. And then finally, again, encourage you to build this village, broad base of mentors. So let's get this started. So key foundations for research. What does it take to do research? And again, many different things that we can talk about here. But the four I want to talk about are perspective. So being informed of your broader context, the broader context motivation for your work. So you need to have this big vision of not only this narrow technical work that you do and where it's headed, but how it relates to everything that's going on in the world. Because that can help you, let's say, for example, when you get stuck on some particular problem or run into a dead end, even in your full technical direction, being able to pivot or being able to relate the work that you're doing to trends and observations that are going on in the broader scientific community. I'd say openness is another one. So this is being able to value alternative ideas and approaches. So in the programming languages community, I have to say, I think we've, the openness in our community has diminished since when I first came into it, perhaps it's now 15 years ago or more, where, and I'll talk about this in a bit, where, so this broad-minded perspective and thinking about alternative approaches, there's a lot of focus now on, this technical depth and soundness and correctness and not delivering anything unless it's, in some sense, perfect, right? And this can at times work at odds with the idea of openness, looking at raw alternative ideas that are out there. And so I'll talk a bit about that. Technical depth, building new skills in depth. And here, what I'm speaking to here is more that I've seen students who feel, let's say, hesitant to get into a new research area, an alternative idea, because they feel that the foundation for that work doesn't necessarily sit on top of their current technical skills. And this is unfortunate, where there are great problems that are out there where what you need to do is try to build these new skills. And it's very common to get outside of your immediate depth to actually tackle that new problem. And then finally, I want to talk about distillation. So mapping these ideas back to a language that your community and your field can understand. So going through these, let's start off with perspective. Be informed of your broader context. So to describe this, I want to talk about my path to programming languages, how I ended up where I am now, or at least where it all started out. And so this started out a very, very long time ago, fall 2003. I was fortunate to be an undergraduate at Stanford, and I took Alex Aiken's compilers class. This is when Alex had just showed up at Stanford, but I took his compilers class. And it was your standard compilers class in parsing to code generation. And it was just such a fantastic class. It completely filled me. I was excited. I was dealing with somehow relationship challenges or whatnot at that point in undergrad. And this class came in and just gave me this great, technical well of ideas and problems that I felt like I could solve. And it really solidified it for me where, I loved compilers. Compilers was what I wanted to be doing, right? And so I took CS243, the upper graduate or the upper undergraduate or graduate level class taught by Monica Lamb. And so we looked at data flow optimizations, automatic parallelization, garbage collection, a wide variety of different, typically performance-related concerns again. And so at that point, this class just sealed the deal. I was in love with compilers. I was in love with the idea of compilation for performance. Now, this is me. Not everyone needs to fall in love completely with the problem, but for me, this is just where I was, and I was so excited about doing this type of work. And so one day after class, I remember thinking, I really want to continue to pursue this and do some research in compilation, with aims to performance. And so I went up to Monica after class and said, I'd really love to do some research. Performance is where it's at. This is the future. I really feel this, right? And Monica immediately responded. Her immediate response was, performance is dead. Right. I always reflect on this response, like how can you just challenge a student like that immediately and deflate their dreams? But Monica, she was right. She said, she challenged me, but she supported me, said, take my CS343. There are all these other things, in this field that are interesting and are coming to fruition or becoming an emerging trend at this time. So if you go back to this time in the mid 2000s, all bug finding, testing, verification these types of things weren't nearly as prevalent as they are now today in our programming languages community. So you have to rewind the clock back to that time and realize that Monica really was broadening my perspective and horizon for what was possible for what I thought was compilation of programming languages work. And the result was I ended up working on a wide variety of actually different projects where I got to work on program analysis, declarative program analysis specifications, where the key idea was we were going to look at programs as if they were databases of facts, right? The fact that a variable points to, points to a particular heap allocation site, right? This can be encoded as a fact. And then what you can do is now compose larger program analyses as just database queries on this database that we have at hand, right? And so this was just interesting, right? It was this idea of just changing your perspective on what a program is and what it was. It changed some of the fundamentals of how we thought about program analysis. And so we started to work on that. And I had this fortunate opportunity as well to still explore performance inside of that, that framework where we're thinking about how do we accelerate static analysis. And what this meant is I got to go and reach back into this compiler background that I had developed thinking about classic data flow optimizations like constant propagation, common subtraction, elimination, and think about what did that actually mean for a database query or a programming language or a little intermediate representation where the operations aren't integer arithmetic as we normally think about in arrays, right? But instead it's actually relational algebra, right? And we're thinking about joins on tables and mapping that to a different semantic. So that ended up being a great change in the perspective that I had. Right. And then finally, Monica challenged me again. So Monica was actually, the first person that got me into machine learning work way back in 2004. And all she said to me, her problem specification was, let's do something with machine learning. That's all she said. It's very open. But I interpreted that she understood at that time that this was a technique that could come in and change some of the way that we were trying to build some of these systems. And in particular, this is a very different style of machine learning than what we see as popular right now. But she still had that sense and pushed me to figure out, well, how do I incorporate an alternative methodology into the type of research that I'm doing, right? And now, so that was Monica, right? She really did push me in a lot of different ways to have a broader perspective on my work, the value of my work, how I went about my work, went into it. But at Stanford at that time, I also had this great opportunity to work with, take classes from, talk to a wide variety of different people that actually showed me that their programming languages, I'll get back to this, was actually very broad in how I thought about it. I got to do some work in the intersection of computer architecture and programming with Kunle-Lucaten. Got to think about scalable bug finding for systems codes like operating systems, file systems, low-level components like that. Zohar Mana and Hemni Sitna, they were pure formal methods people that were in the department. And I got to take some classes from them and really think about true formal methods in a time when formal methods did feel very much like a different domain than, let's say, core PL, as it feels more intersection or more in the intersection right now. Also, John Mitchell, working on types and thinking about program semantics at a more traditional types and programming languages like sense and getting that experience. And of course, Alex was there. He had just started, but he had this wide range of interests from program analysis down to performance. And really the result for me, by working with and thinking about and talking to all these people, I just had this broad perspective that programming language research didn't have boundaries. I feel like this isn't, the programming language community is very broad right now, but it also feels much more siloed than it did those years ago, where I felt that somehow there was this stronger distinction around verification and these types of things. This was all equally valued, and you could move somewhat more fluidly between these different topics. Right? And so it gave me this perspective that my research could be very fluid. There are lots of different problems that I could think about, and it may incorporate a lot of different techniques for this goal of really thinking about computation and programming language's role in computation, perhaps in new and emerging domains. So that was perspective, to develop that broad perspective. And I was very fortunate to have Monica, challenge me, and even challenge me to talk to these other people to develop this broader perspective. So I wasn't so narrowly focused on, let's say, just the one thing that I had been interested in and was initially interested in. It grew to be much broader. So now to the next, openness.
Mike, do you mind if I interrupt with a question real quick?
Yeah, go ahead.
The question from Slido, and Christopher Miller asks about if you have any thoughts about how to find mentorship like that, where you get sort of pushed to challenge, you get this sort of challenging pushback like Monica gave you. Christopher specifically asks outside of the context of academic setting, and that might be particularly challenging, but I'm also interested just more broadly how you find people who will not just agree with you all the time.
Listen. I'd honestly say that, do a lot of listening instead of talking. Outside the academic setting, I've had this very weird career. My wife actually asked me a couple of days ago, it's like, have you ever had a real job? Because I've basically been in academia for a very long time now, either as a student or as a professor. But in my time, at least in Microsoft research, I still felt that was possible, but perhaps the goals were different, right? There you're talking about, end objectives of perhaps making money or whatnot. But if you put yourself on, find people, my goal has always been to find people who are on the forefront of some particular problem or challenge, because those were the hardest settings. They demanded the most of people, and I always felt that, those people could articulate some of the present challenges that are out there. These fields were so new that it wasn't so ossified. Mm-hmm. And so I think that's always worked well for me. Just be on the bleeding edge.
That makes sense.
If it's your company, even finding people that are out there, because you have to understand, to be successful there, you need this type of mentorship.
Yeah. Cool. Thanks.
All right. Perspective. So openness. So value alternative ideas. So the way I like to explain how this has played a role in my research career is during Monica's CS343. This was a topics in compilers class, I think is what it was called, right? And of course, it covered all these broad topics. And the class was essentially run, right? It's one of these great models for running a class where there's a professor who wants to read a lot of papers but they don't have the time to read those papers. So they create a class where they assign the papers to students to read and then give presentations. And ergo, you get to learn about all these papers. And as well, the students have a great time learning as well. And so in this class, I was actually assigned this very unusual paper at the time. So it's called Enhancing Server Availability and Security Through Failure Reduced Computing, OSDI 2004. And this was written by Martin Reimard, my eventual graduate advisor, as well as, of course, his collaborators, a number of other students that are around. And so here's the idea, right? This is, if you haven't seen this idea before, then certainly in the modern context of programming, how we think about correctness, you're probably going to be fairly unsettled. So here we've got this very simple computation over here on the left. So it says compute some value. And what it's doing is just taking some pointer to some integer, reading that pointer, and then returning some function of that value, right? It's very simple, nothing too interesting going on here. Now, so the research question is, what happens if P is 0, right, or null? Right? So if we're talking about in the C++ setting, we should expect this thing to crash, right? It's gonna be a seg fault, right? This is going to fail classically. So now, from that point, there's been this huge work in our community, the programming language community, of avoiding those types of failures, right? Being able to identify, do bug finding, be able to identify that there's a possibility for this type of error and bring this to the attention of a developer. Right, or even to be able to just fully verify that this does not happen, and then be able to have that particular confidence that you have for some particular point in the program. But the unusual idea behind this paper was instead, well, we've got this failure that would happen at line 3 when we try to do reference this pointer. So why don't we just skip line 3, right? Programs are going to continue running. And you say, well, that seems challenging, right? And, one, because you're skipping some code, but then 2, you get to line 4 and you say, well, what are we supposed to do to return a value? We need to return some value. And there, an answer here is, well, just return 0, right? Why not? I mean, that's a value, right? It's an integer, satisfies the type, right? And so at this point, you should be reasonably unsettled, right? And it was an unsettling paper to read, and I'll talk a bit about it, and had a difficult time being accepted. But the thesis of this work was that what you can do is actually make these computations more available, meaning this is going to avoid a crash by using this type of technique. And surprisingly, many programs, computations broadly, can actually tolerate this type of change and still produce an acceptable output. Now, why? Well, if you look in the broader context of this particular program, what might be happening is, compute values be applied to a whole sequence of values. And maybe then there's a big reduction of all those values at the end. So what happens? Well, if I just, one of those values becomes corrupted and I get a null pointer exception in that, and I instead just skip it, what happens is that still I get a pretty acceptable result because there are all these other results that were actually computed correctly. And so this result, this immediate failure actually disappears and you get an acceptable result while avoiding this otherwise fatal crash. Now, when I read this paper, I thought it was very interesting. I was fortunate to be able to be accepted to MIT for graduate school. And so when I got to graduate school, Martin, we were talking about this is very interesting. And he sort of challenged me. He's like, well, this type of stuff is very weird. Do you want to do this? Like, it's very aggressive. We can do this, but it's, it is very different research, right? And in fact, here is a review, right? So this was a snippet from one of the reviews. So he actually just handed me a review from one of the submissions of the paper. And he said, here it is, right? And it said this: I fear that techniques like this will bring on a new dark age in computer science, right? And you can see why this seems very unsettling. How can we let systems go off and do this and not be correct? But for me, this posed a research challenge, a research question. Is it possible to actually enable developers to have confidence in a technique like this, right? There is some value. I wouldn't say clearly there's value. I mean, it's hard, but there's value here. So there's some promise. And the question is, what would it take to make developers confident that this is possible to use this type of technique, right? And of course, we can start to envision the problem, right? You're immediately thinking about how this could be horrible. You might get an inaccurate result, right? You might get correct results too infrequently, get an invalid result, or really what everyone starts to think about is this, nefarious, catastrophic failure that happens because we skipped computing one line in our program. Right? There's always this catastrophic consequence that everyone has in their mind because we've been trained as these engineers to think very adversarially about how our programs can go wrong. Right? But this was a very a fruitful start for this type of effort. Right? A very, very challenging problem. Thinking about the trends in our community and how we think about correctness and what applications should be. And it turned into a challenge for me going forward. And in particular, not only just an intellectual challenge to figure out what these programs are supposed to be, but a technical challenge where I needed to think about the technical depth and develop new technical skills, right? So let's think about that. Let's think about what's going on with this, what we need to be able to do. And I think this is more, in the current context of programming languages, this is more obvious than, let's say, it was when I first started doing these things. But if we want to be able to reason about whether or not these are possible and perhaps eliminate these types of cases from our programs, we want to engage in program reasoning, right? We want to be able to build analyses and whatnot that allow developers to actually ensure that none of these bad things happen, right? And so one way to do this, and let's say in one particular way to do this in a very complete fashion, is by classic program logic. So things like Hoare logic. Right, so if you haven't seen the Hoare logic before, I know we have a wide range in this audience, but the concept behind the Hoare logic is this notation that we have here. So it says P, curly braces S, curly braces Q. And what this type of judgment says, right? You want to prove judgments of this form, where it says if we know that P is true of the program where P is some predicate, then after the execution of S, Q is also true, right? And so as a simple example, if I know X is equal to 1 before executing X is equal to X plus 1, then I can prove that X is equal to 2, right? And so Hoare logic and other program logics consist of a wide variety of rules that allow you to prove judgments like this. And so mapping that back to our problem, we'd want to be able to actually prove that even if you do this crazy thing where you instrument your program to skip null pointers, that you're still going to get, let's say, a correct result, or maybe even an approximately correct result, something that's almost right. And so this type of logical reasoning is really the core that we came to, where we needed to figure out how do we investigate new logics to reason about this. But there was a problem, right? I came from, although I had this great breadth and experience coming from my undergraduate, I didn't know anything about Hoare logic really by the time I was graduating, coming into this project, trying to think about how to make progress here, right? And MIT didn't necessarily help me out so much here. So MIT, they didn't have a PL class at the time, right? And even then, whether or not this type of Hoare logic type work and formal methods would have been in a PL class is open debate. Now our classes do incorporate this, but at that time that just was not there, right? So of course, I read some books, I ended up formalizing my system in Conc, but importantly, I collaborated with a fellow graduate student, which was Do-Kwon Kim. And so Do-Kwon Kim didn't know how to solve these high-level problems, but he was much more familiar with formal reasoning, had more experience with formalizing systems and thinking about logics than I did. Right? And so together, essentially what happened is I would come up with these, I would actually do my homework and try to figure out if something could work. And I passed off to Do-Kwon, and Do-Kwon would say, well, interesting, but this is horribly wrong, right? And then we would iterate and iterate and iterate. So being able to find and work with that peer versus my actual advisor themselves is what got me to an actual solution for thinking about these problems. Right? So, and what was that solution? So, well, if we go and revisit our Hoare logic notation and we change it ever so slightly, what we end up doing is introducing a new concept, new styles of predicates that we want to reason about, as well as potentially some new statements into the program. And so the core idea is that these properties that we want to reason about, it's no longer about just a single program. It's now about two versions of a program, right? It's about your original program, the one that you would have normally written, right? That sits there. And then there's this version of the program that's been instrumented to be failure oblivious, right? And so then what you want to do is be able to describe properties that relate this new program, this failure oblivious program, to this old program. And so, for example, here, there's just some example notation where what I want to say is that the value of the variable X before this statement is the same between, let's say, this failure oblivious execution and the original program. indexed by x angle bracket x, x angle bracket o, respectively. And similarly, I might say something for y. Right? And then there's this fuzz statement. Right? I'll get back to this a little bit later. But you can think about this fuzz statement as, well, I'm going to make up some value for x, right? And then, so after that fuzz statement, what we know is that x may have a different value between the original program and this failure oblivious program, but y is still the same. And so this type of reasoning, where you can think about the interference, let's say, of these failure oblivious mechanisms coming in versus properties that are preserved in the program, means that you can actually now have some sort of compositional reasoning about what is still true of your program, even if you're using these failure oblivious computing mechanisms. And that means that you might actually be able to prove, and in fact, you can, in cases, prove that you still get acceptable results, even though your compiled program is skipping statements as it executes. Right? And so that ended up being the solution there. And again, what was critical there was that, my advisor didn't really have the time or even, let's say, sometimes the technical expertise to be able to work on this problem individually, but by pairing with, frankly, a mentor that I had who was just a peer graduate student, we were actually able to get this problem solved. So now, last one, distillation. So mapping ideas back to the language. If I go back to this little example that we have, this is a really good question of, what is this thing, right? What are we really talking about here? We can say that this is sort of this failure oblivious mechanism that's out there, but really, why do you represent it like this? When would you do this? And are there other things that you could put in here? Is this all just failure oblivious computing, or is there something more, right? And that more that we ended up stumbling upon, as Adrian had mentioned earlier today, was this concept of approximate computing, where these types of fuzz statements were more than just failure oblivious computing, but there was a broader set of things that we could consider if we got into this mentality that, yes, if we change the semantics of programs, if we permit ourselves to change the semantics of programs, then we can actually get all these different benefits. So one being resilience, as we saw with failure oblivious computing, but there's also more. And to explain more and approximate computing generally, I like to use this experiment, this little thought experiment in a little example. Right? So here it is. So this transformation is called loop perforation. And this is a transformation that was developed in the group while I was around while I was a graduate student. And so the idea is that you take your for loop that you have sitting in your program, right? And your compiler is going to come in, find for loops, and then transform them so that they execute for fewer iterations, right? So the question is, the experiment is, well, what will happen to your program, right? So from the failure oblivious model, right, we should be concerned. We've already expressed some of our concerns. And it's not clear that we're getting more reliability from doing something like this, right? But, if you're in this approximate computing setting, as Adrian pointed out, what you can do is you can make things faster and consume less energy, right? If you're in, that's your response. If you're in the approximate computing community, you see this type of transformation, you say, this is going to be good, right? But of course, this may give the wrong result. But as we talked about already in the failure oblivious setting, this is not the wrong result, it's just a different result. Right? And for this, we can actually see how this works. Let's try this out. And this is an example. I don't know how well this has come through on the stream, perhaps not at all. But what is here is we have a single video that's gone through two versions of the x264 video encoder. The video on the left has gone through the standard video encoder. The video on the right has gone through this perforated version, a version where we've applied these types of approximate computing transformations to it. And although there's some minor differences between these two videos, the major difference is that the one on the right is encoded twice as fast as the one on the left. So we get pretty substantial performance improvements by taking this type of approximation, changing the semantics of a program in mind. And so while I was around, we had this fortune to start building these systems. I was only involved in some of these systems, but my group, my group started to get interested in all of these ideas. So when I came into my group, I was the first student. So Martin was doing this phase of switching, where he started graduating a bunch of students, and I was this new student to come in graduate student at least to come in this phase of thinking about these weird failure oblivious programs. And so I came in and, I struggled, I was by myself. Martin was actually on sabbatical my first year. It's all sorts of crazy things that happened. But what started to happen is we were making slow, steady progress, but these other students started to become interested, started to work on these projects, started to take their own directions and do other things. And I'm not going to lie, some of the ideas that I had and thought about, I felt very protective of those. And other students started to work on things that were related. I was concerned, right? I was concerned, particularly if you're struggling, not making progress, like concerned about getting scooped or your projects walking away, right? And that was a very real thing that was happening for me. But really the result was that, together here and also together with Adrian and other people of the community, this idea of an approximate computation started to pop out, right? This what, this why, what are we actually doing in these programs? Where for this variety of applications, what we were doing was exploring this nice trade-off between quality of results and the time or resources it takes to compute results. Right. And what eventually formed, of what Adrian was part of, was this approximate computing community. Right. And as I pointed out, there were ideas I was very protective of. There were papers that other people published that I thought were, I was disappointed that I hadn't gotten there first. As you're growing up and trying to develop as a researcher, it's natural to feel that concern. But when I reflect back on this all these years now, what I start to realize is just how essential all these people in this community actually were to my development, my ability to be able to put up a stronger research contribution that made more sense. There was more evidence behind the contribution, right? And although, some of these people were very direct mentors to me in the sense that we talked about ideas, we collaborated, we worked together, they showed me how to conduct research, but really that building into that community broadly was important and being plugged in there, right? I would not have been as successful if I had continued to think that this was this individual problem that I was going to solve by myself. There's just vastly too much work. Letting people come in and share in these ideas was an absolute success for me. And so what did that success end up looking like? Well, what we did and the methodology we started to use is that we realized, this approximate computing idea was this idea that I had this original program, these transformations, introduced these new points in this trade-off space. Right? And the program methodology that we went about using and I ended up developing was, well, we have our original program. We try to set down a set of invariants that describe in a safe execution envelope. How can this program execute? What is all the flexibility available to this computation? What are the least requirements it needs to satisfy? Then we figure out how to relax its semantics to introduce new behaviors, right? So these approximations. And the final step was to actually verify that these behaviors were still safe, right? And a lot of this methodology, we wouldn't be able to do this without the contributions from many of the people that are coming along in this community, right? And the way that this ended up working out, how was it a success? Well, it wasn't initially a success. So we submitted to POPL in 2012, and people actually, they were receptive of this because now there was all this evidence coming out. So people understood that this is a very interesting, if intellectually risky area. Right. And they really liked the distillation that we were able to do, right? Where we were codifying this methodology as inspired by all this evidence that was out there, right? But of course, that first time it's not always successful, right? And so there were mistakes in the paper, right? And it got worse. They finally just said, no, we really can't do this. Like I'm concerned, right? But on the next time around, again, working with Dokwan, doing a wide variety of different things, we really did have a success there where people, which is one of the reviews that I'm most proud of, it's a necessarily timely and fairly deep contribution to the semantics of such systems. But the important thing, while I'm proud of these, it was not an individual success, right? So along this way, thinking about this community that helped with this distillation process, having these people to talk to refine my ideas, to work through my ideas with, that was critical. Working with Dokwan was critical. Working with Martin, who challenged me to think about these ideas, was critical. Thinking with Monica, to think broadly about what's possible, right? Without that, I would have thought this type of work was valuable, right? So this was in no way an individual success of my own. And there was a much broader community that actually helped me think through the variety of different things that I needed to be able to solve this type of problem, right? And so to conclude, science really, as I keep harping, isn't in this individual pursuit, right? Build a village, right? So peers, as I mentioned, peers are fantastic, right? They're fantastic for emotional support and camaraderie, hack with the deadline to the end. But you'd be surprised by also how much you learn from them, right? And how much they'll teach you and can serve as mentors, even though we typically think of mentors being someone who's senior than us. Right? These people have expertise in their own experience that can help you along your path to be successful, right? Thesis advisors, right? So ideally, you get close advising on your research foundations from your advisor. But as I pointed out, at the bottom of this slide, the responsible conduct of research, right? That your advisor likely isn't going to be able to do it all, right? And so there needs to be more. You can think about multiple advisors, but the writing thesis advisor isn't, signing that form isn't what's critical. You're really looking for someone who's just invested in you being a professional. And there could be many different people that are around that can do that in your department or other places, right? I'd say be in a community, right? So your ideas can reach much further when a community that can build upon the problem, right? Resist this temptation to think of your individual results sitting in isolation. You're going to solve the complete problem. Now, if you're working on a good problem that is hard, it is likely bigger than what you can accomplish by yourself, right? Not only just in 5 years, but even in a full career of research, right? And so these other people coming into the community is important. Being able to support them, have them help you, serve as mentors in that community, and correspondingly for those people to serve as mentors to you, right? So investing in these community activities, right? So for example, Adrian was one of Adrian and Luis Ceza and Daniel Grossman, they stood up some of these initial workshops that we had on approximate computing, which were fantastic opportunities to think about these ideas and distill them. Right? And then finally, senior community members. This is a good one where they're great for non-technical aspects. Let's say things like perspectives, new ideas, or even career modeling, right? So as you're going through graduate school and you're coming up to those last stages of graduate school, you're certainly looking to that next step. Where are you going to land? Maybe it's going to be industry, maybe it's going to be academia. However you think it might be. And you can't, there's this risk, there's this temptation of building this model of your future career based on your thesis advisor. Right? This is the person you perhaps work most closely with, so you think perhaps your life would closely resemble theirs. This does not need to be true, right? And even thinking about the experiences or just broadening that to the experience of faculty at your institution, this isn't good enough either. Right. I have to say, coming out to the later stages of graduate school, thinking about, let's say, the balance of research versus other aspects of my life. I came to this conclusion that I felt like people at some of the institutions that I had been with didn't model this in a way that I thought was going to be reasonable for me, right? It was going to work for me in the long run. And I did. I had to look to other people at other different institutions, try to figure out how they modeled, how they built their life, and if that would work for me, right? So in conclusion, I'd say, one, look at this link down at the bottom. It's a great way to think about mentoring and the challenges you're going to face trying to find a mentor. And finally, just make your mentoring pool as reasonably large as you can, where you're confident all those people that are in that pool are invested in your success. So that's it. And that's it for the talk.
Awesome. Thanks, Mike. I'm going to applaud on other folks' behalf here. You can just imagine that amplified by at least 147, which is the number. We have several questions here, if you don't mind my going through a few of them. One of them is particularly relevant to what you were just talking about up here with like looking for people, not necessarily your thesis advisor who can do mentoring. It's actually from Milland, who asks, building a network seems serendipitous. Who you happen to know or who is around? What can you do if you're in a setting where mentors are not available?
Where I broadened my mentorship pool was at conferences, frankly. You think of some of the people that I think about as being senior people in the field, where I look at their moves, how they've conducted their life. The way I found them was by talking to them at a conference, striking up a conversation. I know inside of PLMW, there's typically these talks around how do you go about socializing and making that easy. And this is something to think about, but many of those mentoring relationships started with those types of same simple conversations, and then seeing that person over and over again, right? And getting an understanding of what their perspective is and whether or not they're open to answering these types of questions, right? And I haven't found any shortage of people who are willing to give their advice, I would say. And then it's just a matter of filtering through that advice.
Yeah, totally. I agree with that. If you don't mind my like stealing a tiny bit of your time to embellish that, I can tell a really embarrassing story, which was about the first time that I met you, Mike.
I think I know what story this
The reason I'm telling
is.
you it's an example of a time when there was like someone at a conference that I knew I had to talk to, that like working on similar things, like absolutely got to get to know this person and like, you know, try to figure out what I can learn from them. And I remember that's super hard for me, as I think it is for a lot of other computer scientists, because like just walking up to someone and introducing yourself is like is surprisingly hard to do. And what I distinctly remember is that I somehow in my mind got two of your letters mixed up in your last name. And like, are you Michael Craben? I think I said. Which still mortifies me to this day. But nonetheless, I'm thrilled that I actually did that, because I was able to learn a lot when we're working in a similar field. So I pray to God that you do not remember that, and I hope that people don't remember like the first time someone introduced themselves to you and made a fool out of themselves.
I don't remember this one, right? I remember later ones, because I mean, from that point, we hung out at conferences all the time, right? I mean, you quickly became a part of my regular social circle, right?
Totally, yeah. All right, so we got a couple more questions here. So here's a big one I think is very, very hard. I don't know the answer to this one at all. How can young researchers distinguish between mentors who create a toxic environment versus mentors like Monica who are trying to push them to do good research?
Oh, oh boy, it's a challenging one. You know, it is, yeah, there's this unfortunate reality that we have senior people in our field that I definitely would not recommend trying to associate yourself with. For me, the recommendation I typically give for students is to go and talk to that person's students, right? You know, look at their outcomes, see where they've ended up, and then try to understand their path. You know, what has been that student's relationship with that person as a mentor, right? So, you know, when students come and visit MIT for our admission days and they say, what is your mentoring philosophy, advising philosophy? And I give them all that. And then I always say, but you have to go talk to my students, because I can say things. And the only way you know that they're really true if they're played out in practice with the students. And so that's what I would do. It's still a very hard problem, but I think that's one way to try to get more information, because I think students, they try a little bit to be more honest about these things.
Yeah, I think you're right about that. So here's another one, sort of on the downer side of things, if you don't mind, which is when you were a PhD student, what helped you to overcome the difficult times? Do you have any suggestions for junior students, presumably on the theme of like getting through the rough spots?
Yeah, it's so village. So there's actually, there's a very specific story for me, where, so in my second year of graduate school, my mother passed away. And this is a massive disruption, right? Of course, obviously, right? She was actually, it was a pretty tragic episode, where I had to go out and take care of her, or participate in her care for some time, for 3 or 4 months or so before she passed away. And while I was out there during that process, you know, my mother, I mean, everyone's mother's a great individual, but I always very much, you know, I idealized my mother in the way that she was actually able to build this village of support, where oftentimes the way she did this was by supporting other people. And so when that happened, there's just this outpouring of support that came from family, friends of family, everyone that was, you know, out across the country while we were out there. And there's no way that my family would have been able to get through the death of my mother without those people. And so when that wrapped up and I came back to MIT, I actually looked around, and I said, you know, if something happens here to me in any way, you know, if it's health-wise, it's not related to technical work, or even if it's related to technical work, right? Who's my community? And I realized that I didn't have much of one. And so I desperately decided that I needed to build one. So for me, getting this support this mentorship. Things like peers help you feel like you're not alone in the problem that you're trying to battle, right? I mean, everyone has a problem, and there's always this risk that when you don't have a very personal community, that students tend to compare themselves against almost like the aggregate students in their cohort, where they see, this person's doing great right now. This person's doing great right now. And it seems like everyone's always doing great. When in reality, you look at everyone's having these ups and downs. So having this closer relationship with peers and people that are in your community can really help you understand that whatever you're going through isn't just you by yourself. And it's everything's uniquely challenging, but there are people there who are also having challenges, and they're struggling with it. They're dealing with it, and they're being successful even despite that, and you can be successful too.
Yeah, great point. I really like that point about comparing yourself to the aggregate. I think we're all guilty of that at one point or another. I still, even though I know that even though I'm constantly counseling my own students not to do it.
Yeah, no, you really have to avoid it. It's hard.
Yeah, great. Okay, so another question we have that's been upvoted several times. You sort of actually answered half of it already. Which says, how do you know if a mentoring community exists when you're applying for PhDs? You mentioned talking to students, but there's some other thoughts about that. But the second half is, can you speak for this community at MIT?
So I would say this community at MIT is it is there, but it's not as formalized, I would say, as you would see at other institutions. But there are other institutions that just do a fantastic job of having a very formalized community where everyone is invested in this community for whatever it is, and seeing all these people be successful, right? So MIT, I think in particular, tends to fall down more on more isolated cliques of people that develop these types of communities. Every so often, we have great people that come in and actually stand broader community efforts up. So for example, Jean Yang, when she was a graduate student at MIT, built all these great institutions that things like our programming languages offsite, where we go on a retreat, things like our programming language lunch that we had as well, right? These were things that she had actually built and put in place and were great and survived. But MIT it's not, I would say it's not representative of all the places. People are exceptionally busy, and that's why some of these things these formal things can get by the wayside unless you have this sustained effort to keep them around. Right? So, but I hope it gets better. I encourage I participate in trying to make it better, and certainly I challenge my students to help make it better because I know it'll help them in the end.
Totally. Here's an interesting question. This one says, you collaborated with a peer with a very different skill set, UPL, than logic. What are your thoughts on making such collaborations work?
It is. So the most interesting thing about that particular collaboration. So Do-Kwon Kim he's one of the smartest people I've ever met, right? And he has this very sort of rigid view of the world. Like everything's very logical, and so it's this weird contrast where he can understand anything, but if it's not logically stated in a crisp way, he's kind of not going to understand it, right? So it's sort of in the limit, Do-Kwon will understand anything. And I realized I had to understand that if he didn't understand something, then there's something wrong with how I was presenting the work, right? And I'd say in any collaboration like that, where you're looking at people that have some skill separation, there's got to be, if you can develop some mutual respect for each other's expertise, I think that's the first one that keeps you guys together. And then iterating through that process, realizing that eventually you're both going to understand what's going on, right? Of course, these things can fall apart. Collaborations don't always work, but I think that's what you're looking for at the outset when people are coming from two different perspectives, is how that final idea, maybe even yielding some ground on your idea such that it sits in this space between you two. Right? Because I certainly take very complicated things out of my ideas to understand them, but once I did, they were very distilled
Right.
and very palatable to work with, right? So Arvind, who is a computer architecture and programming languages professor, he has that he says, if people come to your work and say, I don't understand it, right? It's not their problem. It's your problem, right? You haven't explained it well enough. And I'd suggest, if you can establish a relationship or a collaboration based on respect, putting that mentality on, because it's going to help you make your work better.
Yeah, totally. Yeah, this translation aspect, I think, if you don't mind me injecting my own opinion again, is a sort of like a underappreciated skill in research. As like being able to build connections to people in other areas is hard work. It's not easy whatsoever, but the payoff can be really huge.
Yeah, good collaborations, the work certainly comes out better than if you just done it alone and tried to, crib the knowledge yourself.
Yeah, great. Okay, one more question, or at least maybe more than just one, but this one is how to go about finding a long distance mentor when one is not available around in the area one is interested in.
That's a good one. I've done a bit of this. So I'll say a couple things. So where I've done this is I've had students in the community just ask me questions, right? And they say, I'm really trying to figure out what to do with graduate school in this next phase. Really appreciate your advice. And that was entirely over email where that's happened. So that can be done remotely. But where that has typically started was by, I had met the student, at a conference or a venue of some sort, talked about their work, did the normal social conventions for getting to know and growing your community. And I think in this time, it's a real good question of how you translate this to this time. So I think it's long distance mentoring at some level, at least in the COVID-19 times, is what everyone's going to be doing at some extent. And your real first question is how you engage in that person from the outset to get them invested and interested in you, right? So I think the gather space that we've got for PLDI, I haven't been in it yet, but getting out there, being able to talk to people, have those research discussions, and then from there, figure out what can you communicate over email, because I've had some good interactions with students just over email, being able to advise them on what they're thinking about, because oftentimes the important part is just getting the student to write what they are thinking down, and then you just say, that seems all good to me, right? Of course you have a discussion.
I also wanted to plug a thing we're doing as part of PLMW here to get connected to one-on-one mentoring. We actually set up this, if you saw the statement at the very beginning of PLMW, we're interested in people who want additional one-to-one mentoring. We have a special email alias that you can send to. It's like PLMW PLDI cares, separated by hyphens at googlegroups.com. Anyway, you can find that on the PLMW website. It's a way to get connected to long distance mentoring. And it's part of a longer term effort that the PLMW folks are starting up to address exactly this thing, which is when you don't have mentors locally.
Yes, so do that. I've seen that show up as well. Other versions of PLMW too, with mentoring breakfasts. I think, computer architect community also has this, meet an architect, right? All these types of things are great opportunities. Yeah, so I agree with that. Do that. Do what Adrian said.
Cool. Okay, we are officially out of time. There are other great questions on Slido that we just cannot get to all of them. I'm sorry about that. Maybe we can talk about them in the Slack. I think that other people beyond just Mike might even have ideas about this stuff. Thank you so much, Mike. This is really, really great. I learned a lot, and I want to take some of this advice and learn to be a better mentor as well.
Yeah, thank you for having me. It's great. Hope to see you guys soon.
Round of applause. Talk to you soon, man.
All right.
All right. Before we switch over to the next speaker, I want to remind folks who are tuning in late that we're taking questions for this session over Slido. So if you look at the video description underneath this stream, you'll find a link to the Slido for the entire session. So please ask questions there. Our next speaker, whom I am thrilled to introduce, is Professor Amal Ahmed from Northeastern. Like Mike, Amal has been the recipient of many fancy awards, which I will not attempt to list here. But one important thing about Amal is that she is a member of the PLMW steering committee. For personally speaking, for a good long while, I've been interested in her work about interoperation between languages and modularity in general, about reasoning about programs. And this, I read the abstract for this talk, which I'm very excited about, which has some flavors of that, but taking into a new compiler verification type of direction. So please take it away, Mo.
Thanks so much, Adrian. Okay, let me just share my screen. Okay, is that visible?
Yes, visible to me.
Okay, great. All right, so this is a technical talk, and what I'll be talking about today is compositional compiler correctness. Let me just start off by talking about, well, what is compiler correctness in a nutshell? So let's say you have a compiler, and at a very, very high level, let's say it compiles some source program S into some target program T. I'm going to use the letters S and T for that throughout this talk. What you want to show is that this compiler is correct, which basically means you want to show that the source program S behaves the same as the compiled version T. So that both source and target have the same behavior. Compiler correctness is the name that we use sort of informally. More precisely, what we're after is semantics preserving compilation. So what we want to say is that if you run the source program using the source language semantics, and you run the target program using the target language semantics, then the observations that you see as those programs run will be the same. So that therefore the semantics are the same. So compiler verification is a really old problem. It's one of those big problems of computer science. It goes back to this paper, which is now more than 5 decades old. So a paper by John McCarthy and James Painter called Correctness of a Compiler for Arithmetic Expressions. So in this paper, McCarthy and Painter showed how to take a very, very simple compiler for a language that only had arithmetic expressions, compile it to machine language, and show that it was correct. Now, since '67, there was a lot of work on compiler verification, but I would say that the sort of, there's been a renaissance in compiler verification since this 2006 paper by Xavier Leroy on Comcert. So what is Comcert? Comcert is a C compiler, an optimizing C compiler that has been implemented using the proof assistant Coq and has been verified simultaneously as it was implemented. So before Comcert happened, nobody really believed that you could take an entire compiler, especially an optimizing compiler, and actually go and verify it, have a machine check proof of correctness of the whole thing. So this paper was a real, this paper and the work on Comcert was a real eye-opener for people. And what it showed is, it demonstrated that realistic verified compilers are feasible and that they bring tangible benefits. In particular, the tangible benefits part, I like to put up this quote from this paper from PLDI 11 by Yang et al. So what this paper did is they had a tool called CSmith, which essentially generated a whole bunch of C programs, and they subjected, C compilers, Comcert, GCC, LLVM, et cetera, in order to find wrong code errors in these compilers. And there's this paragraph about Comcert, which says that the striking thing about Comcert results is that the middle end bugs we found in all other compilers are absent. So even GCC and LLVM, which were far older compilers. As of early 2011, so this is an old paper, a 2011 paper, Comcert is the only compiler we've tested for which CSmith cannot find wrong code errors. And this is not for lack of trying. And then they say the apparent unbreakability of Comcert supports a strong argument that developing compiler optimizations within a proof framework has tangible benefit for compiler users. So this was really heartening, that if you put in all of this effort in order to verify your compilers, you really are getting tangible benefits. You're getting compilers which are more robust, correct with certainty as compared to compilers that have been, worked on for far longer. The other amazing thing about Comcert back then was that it provided a proof architecture for others to follow and build on. So this led to a lot of work in the following years. And this, what I'm showing on the slide here is just a few of those papers. So people started using Comcert's basic proof architecture, the methodology, to do all sorts of other compiler verification. This work on compiler for Java threads, just-in-time compilation, extending Comcert to compile down to relaxed memory models. Trying to use that methodology to verify passes, major passes of the LLVM compiler. And then there's this work, very nice work on CakeML, which is a verified ML compiler. But one issue with all of the results, at least that I'm showing you on this slide, and Comcert as well, the original Comcert, is that when they prove compiler correctness, they all make a whole program assumption. Okay, so what that means is that the compiler correctness theorem that they prove, its correct compilation guarantee only applies if you are compiling a whole program. So throughout this talk, I'm going to use this capital P to indicate that I'm talking about a whole program. So PS is a source program, PT is the whole compiled version, the target program. So if you have a, but the reality is that when we compile programs that we write, we rarely ever compile whole programs. Even when we think that we're writing a whole program and compiling it, that program will be linked with some sort of low-level libraries. And in the more general case, we frequently these days build software written in multiple languages. So you might implement one component of your software system using a language that I'm calling S, which is blue here, and another component in some other language, let's call it R, which might be that red piece there. And then you take these components written in different languages, you compile them down to the same target and link them together. So what we'd like to know is that if you compile this source component, and I'm writing this letter E to just indicate a component or an expression as opposed to a whole program, when you compile a component from source to target, is your compiler still correct? Which means that your compiler correctness theorem needs to somehow take linking into account. So why is it that Comcert and all of this follow-up work that I was showing you earlier made a whole program assumption? Well, so let's take a look at how this relationship is expressed. So what we want to show is that if S compiles to T, then S is equivalent in behavior to T. But how is this equivalence, this S equivalent to T or behaves the same as T, actually expressed? Well, so in the case of Comcert that follow-up work, Comcert uses a simulation relation in order to express this relationship. So here I'm talking about whole programs, and basically the way that you establish that PS and PT behave the same is, well, in a nutshell, you're saying that if I run PS, then I'm going to see the same behavior as when I run PT. Technically, though, you come up with a simulation relation R, and you show that if your original program PS is related, well, first you show that your original program PS is related in your relation to PT. And then you show that if I'm at any point, after having run some number of steps, if this PSI is related to some PJT, then if my source program takes one step, then my target program will take one or more steps, and things will be related according to my relation again. Okay, so this is called a closed simulation, closed because we're talking about whole programs. The nice thing about this kind of proof methodology is that these simulations compose really well, so that you can prove the correctness of of each pass of your compiler, and then put those together. So here, what I'm showing in the figure is, suppose you're compiling from source language S to some intermediate language T, and then from T to U. For the first pass from S to T, we would show that we have a simulation and therefore show correctness of that pass. We would do the same thing for the next pass using a different relation, but these relations compose, and so you get an end-to-end compiler correctness result for your multipass compiler, that if PS compiles through PT, to PU, then those two are going to behave the same. So these simulations compose really well. And of course, all realistic compilers are multipass compilers, so this is an important consideration. So now let's talk about what happens to the world when we're trying to compile components. So if you're trying to compile a component ES to ET, right? Now you want to show that ES behaves the same as ET. But how do you express that behaves the same or equivalence kind of relationship now? And the issue is that ES and ET are not whole programs. So what do we have to do in order to think about, they're not whole programs, so we can't run them like we were doing before, right? Before we were saying if you run the source program, you see the same behavior as when you run the target program. Now, in order to run the target compiled code, you have to first link it with some other code. I'm going to use the letter ET prime pretty much throughout this talk for you, and I want you to think, every time you see that, I want you to think of the other code that someone's going to give us that we need to link our compiled component with. Okay, so in order to run ET, I need to first link it with some ET prime in order to get a whole program, and then compiler correctness should tell me that when I run ET linked with ET prime, then I should see what? I should see the same behavior as ES linked with some representative, something that's the same as ET prime, right? And this question of what that something is, what that gray box is really at the heart of why proving correct compilation of components is so hard, and it'll really be the focus of the rest of my talk, I'll slowly explain how different results approach this. So this area is called compositional compiler correctness because it's about components that need to be composed with other target level components in order to run them, in essence. And when you're proving these kinds of compositional compiler correctness results, so correct compilation of components, you have a choice as the compiler writer, the compiler verifier, about the theorem that you're proving. You could choose to say that I will only allow linking with ET primes, with this other code, that is produced by the same compiler, my verified compiler. That's not a very interesting result, I would say in some ways. It's what I would call a separate compilation result, but not a very general compositional, linking with anything kind of result. Another choice you could make is I am going to allow linking with ET primes that come from a different compiler, but for the same source language S. Another possible choice is you could slowly get more liberal here. I'm going to consider ET primes that were produced by a compiler for a different language. Let's call it, this is my other language, I'm going to call it R. So my source language for my verified compiler is S, and I'm allowing linking with code that's compiled from a language R. And even that can be split up into two categories: a different language R, or a language R that's very different from your source language S. And by that, what I mean is that a situation where the behavior of the code, this ET prime that you're linking with, is not even expressible in your source language. And I would say that when we build multi-language software, we ideally would like to be able to support linking such as that. Okay, so I'll come back to that. And really, what we want in this space, just to reiterate before I jump into details and results, we want to verify realistic compilers. And by realistic, what I mean is we want to be able to link with code that comes from other languages, so code of arbitrary provenance in a sense, and we want to be able to verify multiple passes. So whatever this definition is, this ES behaves the same as ET, however you specify it, you have to be able to, or it would be nice if you were able to, support both linking with software from code from other languages and compilers with multiple passes. Okay, so I pretty much just said that. Permit linking with code from other languages and verification of multipass compilers. So in the next part of the talk, I'm just going to survey sort of the main results in this area, the state of the art, if you will. And what I want to focus on is how these different compositional compiler correctness results express this relationship between a source component ES and a target component ET. How do they say that they behave the same? And how you specify this equivalence between source and target programs, this property that you're setting out to prove, then has consequences on several things. Well, first of all, one needs to pay attention to how restrictive is the linking policy. What can we link with? How do we check if someone gives me an ET prime, is it actually okay to link with? Can I actually check that in an automated way? What is the effort required to prove transitivity in order to get your multi-pass compiler correctness, end-to-end compiler correctness result for a multi-pass compiler? This is often called vertical compositionality, and linking is often referred to as horizontal compositionality. And then a final point that actually is very interesting is if you are a reviewer of a paper on a compositional compiler correctness result, what's the effort required to have confidence in the theorem statement? And this will make more sense when I get towards the end of the talk and you've seen a few results. So let's dive in. What I'm going to do is I'm going to show you sort of a linking line along which we and talk about results on this linking spectrum. So the original Comcert allowed us to link with nothing. I'm going to talk about SEP Comcert briefly, which allows you to link with ET primes with other code that is produced by the same SEP Comcert compiler. Okay, so the SEP Comcert work takes Comcert and extends it to essentially a separate compilation result. Then I'm going to talk about Pilsner, which allows you to link with code that was produced by a different compiler, but effectively a compiler for the same source language S, the source language for which you are building a verified compiler. Okay. Then I'm going to talk about Compositional Comcert, which is a variant of Comcert that's set out to allow linking with code that comes from that's compiled from a different language R. Though in this case, I think that R ends up being equally, it is code that could have been expressed in your source language as well. And then finally, I'm going to talk about this multi-language approach to proving compositional compiler correctness, which is my my own work, which allows linking with code that comes from a very different language, or in particular a language in code that you could not even have written in your source languages. Okay, so let's talk about CEP Comcert. All right, so CEP Comcert, as I said, is a separate compilation result. So what it allows is that if you have a bunch of different modules, the blue pieces, and you separately compile them to the target code, the purple pieces, then you, when you link them together, you basically have a correctness result. So linking with any other code that was produced by the same CEP Comcert compiler is fine. In their paper, they proved two notions of correctness: a level A correctness, which says that all of these source components were compiled using exactly the same passes. They undergo the same transformations and the same optimizations all the way down until they get to the target. And they also prove a level B correctness, which is slightly more flexible, in which they say the code, so I'm going to, I can use compile one component and do certain optimizations in this RTL phase of the compiler, but I can compile a different component and not do some of those optimizations, and I will still support that linking. Okay, so basically you can omit certain intra-language optimizations in one pass of the compiler, which gives you a little bit of flexibility. Okay, so I'm not going to say a whole lot more about CEP Comcert. Let's move on to Pilsner. So Pilsner I've characterized as allows you to link with code that comes from a different compiler but for the same languages. So let's see, what is Pilsner's philosophy? So remember, we're trying to say, if you have a source component ES that compiles to ET, how do I specify ES as equivalent to ET? And Pilsner does this using this approach that I would call an approach based on cross-language relations. So what you do at the outset is you sit down and you specify when is any shape of source component, source expression, if you will, to be considered equivalent to some target code. So you actually write down a full specification using a logical relation. So it's a relation that's relating source components to target components. And the word component here is I'm using rather liberally. You could interpret it as an expression, as a module, etc. In this case, it's expressions of the language. So cross-language relations actually go back, have been around for a very, very long time. In the PL literature, people have used these cross-language relations that specify when source and target of a translation should be related to verify lots of different translations. But this approach really started to be used in more realistic settings with these two papers around 2009 and 11, which these cross-language relations were used to verify single-pass compilers for ML-like languages. Okay, now single-pass compilers. All right, so these two results that I just had up there, they don't support transitivity, because in general, these cross-language logical relations don't support transitivity. The issue is that if you compile some source to some intermediate and then the intermediate to a target, you have two relations between source and intermediate and target, and you somehow want a single relation between source and target, and that ends up being hard. Follow-up work by Nice et al. Is this work on Pilsner that I'm that I'm talking about now, or would like to talk about next. This work took the traditional cross-language source-target logical relations approach and generalized it in a way so that you could prove transitivity. Now, proving that, so that you could verify multipass compilers. Now, proving that transitivity is possible using these parametric interlanguage simulations. Essentially, they're also cross-language, interlanguage, cross-language relations. But proving the transitivity still requires effort, but it is possible. So what Pilsner did is it used this Pils relation approach to verify a two-pass compiler. Now, what I want to talk about is, what is this cross-language relation? What is it saying really? And therefore, what are its pros and cons? So let me try to sort of give you a high-level view of what a cross-language relation is really saying on this slide. So what I have here is that, suppose you have a source component ES, and I'll say that, let's say it's from a typed language, it has some type tag, just to keep things simple. In order to express the fact that ES is not a complete program, I'm assuming that there's some free variable x in this component. I think of that as my slot where I get to plop in some other code that I need to link with, right? Or substitute in for that variable in order to get a complete program. So I'm just trying to say that ES is a partial program. It has a free variable x, which is where you can plug in some other code. Now, if we compile ES to ET, I want you to think of this purple ET as having a purple variable x where I would plug in some target code, okay? So if we compile ES to ET, then we want to show that ES is cross-language related to ET or PILs related to ET, right? So this is the specification of when source code is related to target code. So what does this definition say really? In a nutshell, what this cross-language relation says is something like this. It says, for all ES prime and ET prime such that ES prime and ET prime, these are the other code that you're going to link your ES and ET with. If you give me some ES prime and ET prime that are cross-language related, then I can link ES with ES prime, right? Substituting ES prime for X here. And I can link ET with ET prime, substituting the ET prime for the purple X that I said was there, in order to get a whole program. And those will be cross-language related. Okay, so you give me two related things, I can plop them in and get related whole programs. Okay, related meaning equivalent, same behavior. Okay. So let's take a look at how we would use this. Suppose we have a compiler from ES to ET, we compiled it, and we have a theorem. We have a verified compiler, so we have a theorem that ES is related to ET. Now, suppose that someone comes along and they give you a component to link with. It's ET prime. So someone gives you this blob of assembly code, ET prime. How do you know whether your compiler correctness theorem allows you to link with ET prime? So this is normally in-person talks. I would wait here, but maybe today I won't. But I'll pause a little to let you think about it. How do you know that it's actually okay to link with ET prime? Is that okay according to your compiler correctness statement? So let's take a look at the compiler correctness theorem, right? Does the theorem permit linking with ET prime? What is the statement? The statement is right there, right? I am allowed to link with these ET primes as long as there is some ES prime that's related to it. So in other words, in order for me to know whether it's okay to link with this code that you gave me, ET prime, I first need to come up with an ES prime, and I need to show that it is cross-language related according to the same relation to the code that you just gave me, right? So, and then of course, I get the result that I want. But this is highly impractical, right? You need to come up with a source component, ES prime, that's related or equivalent to some target code that you'd like to link with. And this is not feasible in practice. And the other problem is that you cannot link with any ET prime whose behavior cannot be expressed in the source, right? And I would actually say that the second point perhaps is less important. You as a compiler, verification, you as a person verifying your compiler might make a choice that I don't want to allow linking with code that can't be expressed in my source. Fine, that's a choice. But I think the first problem is really far more significant, right? There's no automated way for me to tell that given a blob of assembly code, this ET prime, is it even within the purview of my compiler correctness theorem? Is it within that circle that a theorem draws around? These are the ET prime, the other code that I'm okay linking with, right? So you can't check that in an automated way. So that brings me to this interesting observation. So in the compiler correctness literature, or in the compositional compiler correctness work, people have been using the term linking and horizontal compositionality to be roughly the same thing. Linking, right? And horizontally composing. So, but let me just sort of draw a picture to say what I think these should mean, all right? Horizontal compositionality in a very PL sense should, when applied to compilers, should give us something like this. It should say that, okay, I know that ES and ET are related according to this cross-language relation between source programs and target programs, or source components and target components. If you give me another ES prime and ET prime that are also related by the same relation, then I will be able to horizontally compose the two, and I will get that ES composed with ES prime is related according to our same S and T relation, source target relation, with ET composed with ET prime, so composition, right? The composition is related if the pieces were related. This is what I would call horizontal compositionality. But I would claim that when we do compositional compiler verification, we want a slightly different property. Because we want to be able to link with an arbitrary, with some ET prime given to us, and we don't necessarily have the ES prime for it. So in other words, what we want is, we want to be able to say that ET linked with ET prime behaves the same as ES linked with that same ET prime. So in other words, I'm going to call this source independent linking. I don't want to have to come up with some source representative for my ET prime. I just want to say that target level linking of ET prime is going to behave the same as, morally speaking, the same as ES linked with ET prime. Now, of course, this high level picture has a problem, right? So I'm claiming that this is what we want in order, because that better matches the use case, the way that we use our compilers. But the problem, of course, here is, well, this is a source target relation relating source code to target code, but what is this, right? Here suddenly at the top, I'm putting code that is a mix of source and target, blue and purple, right? So what is the language even on this side now, right? And obviously we need to say what it means to mix source and target code in this way, if that's what we want. So that leads me to the next two pieces of work, which do exactly that. They give a meaning to what is source target linking so that they can do what I call source independent linking on the last slide. Okay, so first, back to this issue, right? We ES composed to ET. We want to be able to say that ET linked with ET prime behaves the same as ES linked with ET prime. And of course, the problem is that you need a semantics of source target interoperability. Compositional Comcert defines something to do this that they call an interaction semantics. And the multi-language source target multi-language work defines the source target multi-language. And I'll talk about both of these results next. So first, Compositional Comcert. So as I said, Compositional Comcert defines something called an interaction semantic. So this is a figure from their paper. It's far too scary, but let me just sort of zoom in on what I'm trying to say with it. So they define this idea of language independent linking. Now, what that means is I want you to think that your component is the blue stuff right here. So they give us semantics. You can start off in an initial state, then you're running. You can interact with other code. I want you to think of that as the orange code here. And there are certain invariants that need to hold sort of at this boundary, which I'll talk about briefly. So they essentially give this interaction semantics, which in a language independent way that allows you to run code, your component, your language, with another component, blue stuff with orange stuff, if you will. So in addition to this specification of language independent linking, they set up something called structured simulation. So now let's go back to Comcert for a second. Remember I said that Comcert specifies a simulation between source and target. Okay, and that you could compose simulations. But now in a compositional compiler correctness setting, what Comcert needs to do is, what Compositional Comcert needs to do is they need to specify a simulation relation that a single simulation relation that they will use to verify every single pass of the Compositional Comcert compiler. It has to be the exact same relation, otherwise transitivity won't work and you won't get an end-to-end compiler correctness result for your multi-pass compiler. So what they do is they set up a structured simulation that supports this rely guarantee relationship between all the different languages that are sitting in the Comcert pipeline, all right? So this stuff is really hard, and let me try to explain why. In Comcert, there are some passes which do memory injections, where you have a big chunk of memory that's being collapsed down to something small, and memory projections, big small chunk of memory being expanded into something big. And now what I'm saying to you is that you need a single relation that works for all of these passes, which means that you have to do some really, clever thinking and work in order to figure out, in order to unify into a single rely guarantee relationship, what is going on in every single pass of the Comcert compiler. So coming up with a relation that is, satisfied by every pass of the compiler in some sense. It has to be really general. And that is a lot of work. And of course, there is a drawback to this, right? This transitivity then, so since you use a single relation, then it can be composed and you get a multipass compiler correctness result. But the problem is that suppose you came along tomorrow and you decided to insert one more pass. You tried to do some sort of fancy optimization and add a new pass, and maybe this involves memory. That's usually where the trouble is. But it's some sort of an optimization that changes memory in a way that no longer satisfies the structured simulation that you had chosen to verify all your passes with. So that means that you're going to have to go back to the drawing board and kind of redesign a new simulation relation that generalize it so that it fits this new pass, and redo verification work. So that's the kind of drawback. You rely on the restricted set of memory transformations that you can see now. You set it up, you do the work, but it may not be extensible to future fancy optimizations. The other thing to point out about this is something I haven't mentioned is one of the real, the beauty of Comcert, the reason it has worked so well and so many people have built on it, is that the Comcert compiler has a uniform memory model across all of the languages in the compiler. And that simplifies things in a certain way, which has been, really helpful for various verification efforts. But it's not clear then how to extend the language independent linking methodology. Is kind of based on the fact, or takes advantage of the fact, that Comcert has a uniform memory model across all languages. So it's not clear how you would scale this kind of an approach to richer source languages, such as ML, because then you'd end up with different memory models for your source and target languages. So how do you scale it to languages which have different memory models? So those are just two observations about Compositional Comcert then. Let's go on to the next approach, the multi-language, source target multi-language approach. So this is work that one of my students and I did. What we were after principally was this question of, I want to allow linking with code that cannot even be expressed in my source language. That was a specific goal. So what was the methodology? Well, in order to specify what it means to mix source code with target code, this ES with ET prime, we specified semantics for source target interoperability. Okay, and the way we did this is using this multi-language semantics approach by Jacob Matthews and Robbie Findler from 2007. And basically, what you do is you take your source language and you take your target language and you add to those languages two boundaries. The ST boundary, which allows you to take target code, a target component, and put it in a source context, and the TS boundary, which allows you to take source code and put it in a target context. Okay. And then you give operational semantics to these boundaries, and that gives you a definition of what it means for source target components to interoperate. So then where I had ET prime here before, in the multi-language approach, you can just replace that with ST, this ST boundary wrapped around the ET prime that we are given. Right? And that gives you a sensible semantics of interoperability between these two pieces. And then what we want is, from our compiler correctness result, is that ET linked with ET prime, right here, should be contextually equivalent in this multi-language to ES linked with ST ET prime. And then I put a TS around the whole thing because I have target code on this side, so I want to say I have target code on the other side. Right? But this contextual equivalence is the natural equivalence that falls out for the multi-language now. What does it mean for any components in that multi-language to be to behave the same, to be observationally the same? ES equivalent to ET prime. This is defined as using this multi-language contextual equivalent. That any source component ES is equivalent in the multi-language to ST wrapped around ET prime, which means that you can put this component or this wrapped component in any larger program with a single hole in it. Okay. So we can extend this approach to multiple languages. When you have a source, an intermediate, and a target, in a straightforward way, you would define a single multi-language SIT that mixes all of these languages together by giving boundaries between successive languages. So SI and IS between the first pass and IT, TI between the second. And then you can prove compiler correctness by saying if ES compiles to EI, then ES is contextually equivalent to SI boundary wrapped around EI. But what I want you to note here is that this equivalence is the equivalence of the entire language SIT, not just S and I. Okay, and similarly for the next pass. So you can get to multi-pass compiler correctness because we're using the same source intermediate target SIT equivalents for this pass and for this pass. And therefore, we can show that if we verify the first pass and we verify the second, I can throw an additional boundary around this and get that ES is equivalent, because contextual equivalence is transitive, ES is equivalent to SIIT wrapped around ET. SIT is just shorthand for what I have written over here, the two boundaries, the composition of the two boundaries. Okay, so that's how you get multi-pass compiler correctness. So you can now, in a multi-language setting, you would put SIIT wrapped around the given code ET prime, and that would be your compiler correctness result, or the consequence of your compiler correctness result. So we applied this approach to a functional language in order to see how do we even do this, right? And there are some really difficult challenges. One being, what is interoperability between an assembly language and a high-level functional language, ML-like? That actually ended up being a very challenging problem that we initially wrote a paper on the first pass, 2 passes, and then extended this work to, interoperability between assembly and functional high-level languages, which is interesting in its own right. So what we did, though, is we followed this approach used by a classic paper from System F to Typed Assembly Language. If you haven't read it, I highly recommend it. Back from around 2000, 98, 2000, Greg Morissette and his students did this work. Where they built a type-preserving compiler from a functional language, but all the way down to a typed assembly language. And the idea here is that each one of these passes does a type translation. So I take the type of a source component and I translate it to get the type of the target component. And I do this across every pass. So just to sort of fill in this picture a little bit more, to tell you one bit that I didn't say before, the boundaries that we define, so between F and C, which is the target of closure conversion, and then we do heap allocation and then assembly, the boundaries that we define, each of these, are always mediating between this type on the source side, and on the other side, we require that the target component always have the translation type, the same translation type as the one that we are using in the compiler. Essentially, what that translation type is capturing is the calling conventions, if you will, after compilation. So boundaries mediate between types and the translation of those types. When we give operational semantics to the boundaries, the general idea is you want to say that if you have an expression under a boundary, you run that expression down to a value using that blue language's operational semantics, and then you do the interesting bit where the boundary converts the blue value into an orange value. And vice versa. Okay, so that conversion would be, if you had, let's say, the number 5 in the blue language and you need to convert it to binary or something in the orange language, you would have 101, that sort of conversion. Or if you have a true in here, then you would convert it to a true in the other language. Now, it's not that any operational semantics for multi-languages would suffice. Your multi-language has to be set up so that it satisfies at the very minimum this property, well, several properties, but this is the most important one, this property called boundary cancellation, that if I take a component and I wrap it in a boundary going one way and then back, then that should be contextually equivalent. It should have the same behavior, observationally speaking, when embedded in a larger program as the original component. Okay, so we call this boundary cancellation. And it's only if you have boundary cancellation that you have set up a multi-language semantics that you can actually use in the statement of a compiler correctness theorem. Okay, otherwise it's not kosher to do so. Okay, so I've already said that this result, we explicitly were after showing that once you've proved compiler correctness for a multi-pass compiler, you will be allowed to link with code whose behavior cannot be expressible in S. And we show an example of that in the paper. But I'd like to sort of talk now about the effort required to prove the correctness of a multi-pass compiler, to get this thing called vertical compositionality or transitivity. In other words, I want to verify each pass one at a time, but then I want to be able to compose them to get an end-to-end compiler correctness result for my whole multi-pass compiler. So these results, Pilsner, Compositional Comcert, and the multi-language approach, they all have to put in a lot of effort either proof effort or engineering effort in order to get the kind of transitivity we need, right? And at this point, it's worth sort of, again, examining, just like we did for horizontal compositionality and linking. What do we mean? What do we want? Let's take a look at these two words in the context, and compare what they might mean. So if I were to just act like a PL person and say, I want vertical compositionality in this setting, what we'd be saying is that if a source component compiles to an intermediate component, ES compiles to EI, then I'd like to be able to verify that pass without thinking about any of the other passes in my language. So in other words, it would be nice if I could just set up a relation between S and I and not have to worry about what T or other languages might come later in my compiler or higher up earlier in my compiler, right? Just truly just being able to think about that pass, one pass at a time. And similarly, just I and T, right? And if I could verify each pass alone in isolation without worrying about what the other languages in the compiler are, I would like to then be able to put them together and say, oh, ES compiled to ET is actually equivalent according to this third relation, but this one now needs to relate S directly to T without talking about the intermediate languages I that might be sitting in the middle, right? So this is what I would say is what comes to mind when you say, oh, I'd like vertical compositionality, the ability to not have to think about the other passes in the compilation pipeline when verifying correctness. But what we actually do is a bit of a cheat. Both Compositional Comcert and the multi-language approach, my work, we both we technically prove transitivity, but we don't have this nice vertical compositionality because what we're doing morally is we're verifying each pass using the same relation. In the case of the multi-language approach, this is the relation that talks about all the languages in the multi-language that mixes S and I and T. So the intermediate language is part of this specification. In Compositional Comcert, remember I said they set up a single structured simulation. You can think of that as this relation SIT that they use for verifying every single pass of the Compositional Comcert compiler. So they're essentially doing the same sort of thing that we are with the multi-language approach. And this shows you that there is a tension, because you're trying to establish an equivalence. How can you ignore languages? How can you just think about S and I? Because language T that comes into the pipeline later might affect my equivalence in really drastic ways, right? And target languages like assembly, are generally far more expressive. You can write code in there which will disrupt equivalences and invalidate optimizations that you thought were equivalent before when you thought, oh, I'm never going to link with assembly. So vertical compositionality and transitivity are, transitivity is a trick. Vertical compositionality seems like it's what we want, but it seems really difficult to achieve. So what I'd like to leave you with, well, it's not my last slide, but what I'd like to sort of emphasize.
Sorry, can I just interrupt with a quick question here that we got from Fido? The question is about the sort of transitivity stuff with vertical compositionality. And the question is like, how automatable is that type of a proof? That is like, is it ever possible to automate these proofs of transitivity, or is it never possible, or is it sometimes possible?
So, well, automatable, let me just try to interpret that. So all of these proofs, when we prove compiler correctness, they're not automatable as such, right? We go in, we use coq, we verify that the compiler is correct. But maybe there's a sort of other interpretation of automatable here, which is that, yeah, could we, now I'm trying to interpret the question a little bit differently. Could it ever be possible that we could, do that we could verify just the S to I pass without thinking about T? I wonder if the person wants to chime in and add to the question. And that's
sort of what I was thinking, for what it's worth, is that.
Yeah, exactly. And so the answer sort of is no, right? When would it be possible? If we just sort of theoretically think about when would it be possible? It would only be possible. So there's a technical property, actually. If your compiler satisfies that, then it would be possible. So suppose that you are trying to build a compiler that insists that you never allow linking deep at, down at the target level with any code that could not in some way already have been expressed in your source language. Maybe it was expressible only in a really unoptimal, inefficient way, but still expressible. If you could restrict linking to only code that is somehow expressible in your source language, then that is what we call a fully abstract compiler, right? It's restricting the power of, or the expressivity of the target languages that you're allowed to link with, which means that I could verify the S to I pass because I know that I'm never going to be linking with more expressive code that might disrupt my equivalences, the one that I assumed for the SI pass, later in the compilation pipeline. But that's a restriction. And actually, I'll point you to a paper in a couple of minutes, which talks about precisely this question and says, how do we get vertical compositionality? It's a functional Perl that sort of hopefully will illuminate some of this. So what I want to say, and I'm probably going to skip a couple of slides after this one, is here's the landscape that I've shown you. Okay. Pilsner satisfies horizontal compositionality, which I claimed is not what you want. You want source independent linking. And it satisfies, but it does satisfy good vertical compositionality. You have to do a lot of proof effort, but basically what they're saying is they're setting up across the language relation between S and I and between I and T, and then they're setting up a third one between S and T and showing that the composition of SI-IT gives you the ST equivalence. A lot of proof effort. What Compositional Comcert and the multi-language approach did is they did engineering work to set up a relation for which transitivity would then trivially fall out. Okay, so upfront work, transitivity falls out. But they do give you source independent linking. And the reason I have this sort of grid up here is because I want to show you that we really want to have vertical compositionality for the compositional compiler verification space. I claim that what would be ideal is we want source independent linking and we want vertical compositionality. These two are at odds, though. If you study these results very carefully, they are very much at odds, and it's very difficult to sit in these two boxes at the same time. And so there is a need for new ways of thinking about this problem and new proof architectures so that we can get results which are sort of more modularly verified, which is what vertical compositionality is about, but also don't restrict you in this, to horizontal compositionality, where you have to come up with some source component that expresses the behavior of some target component that you're linking with. Okay, let's talk about if you're a reviewer, what do you need to do in order to understand if any one of these results is correct? For Pilsner, you have to understand, you better go and look at and understand the entire source target Pils relation, because that is the specification. That specification is built into your compiler correctness theorem. Right? So in this world that we live in, where we go verify everything in Coq, and then, reviewers are often very happy. Oh, the whole proof is verified in Coq. Yes, the proof is, but is the statement correct? Right? And that there is no way that we can avoid looking at the statement, and the statement now includes this very gigantic source target Pils relation. For compositional Comcert, similarly, you need to understand the interaction semantics and structure simulations. Humans need to look at it, need to discuss it with each other and say, did they get it right? Similarly, for the multi-language semantics, you need to look at the source target multi-language and make sure that, they got it right. So basically, whenever you start talking about correct compilation of components, you have to somehow specify, some way of, capturing the equivalence of these components. And these are all massive specifications that get you there. But they are massive. And so, we ought to be treating them with care and reviewing them very well. So that led us to this question. Is there a generic compositional compiler correctness theorem that we could give to the community and use it at least as a conversation starter and say, here is what we want? How do each one of these results that exist and their particular ways of specifying compiler correctness, right, whether using a Pils or structure simulations or source target interoperability, how does that fit into the general statement that we think we as a community want? So I'm just going to walk through this really, really quickly. And this is, given in this paper, this is a functional Perl that we had last year at ICFP. It's called the Next 700 Compiler Correctness Theorems. It basically, covers some of the results that I've talked about in this talk and some more. And it expresses a generic CCC, compositional compiler correctness theorem. Essentially what this theorem is, it's going to be parametrized with various things. So I'll just try to quickly walk through it. What do we want? How do we express this? Well, all of these results, any compositional compiler correctness theorem that you want to state needs to say, what are you allowed to link with? So you need to say what your ET prime is drawn from. And I'm going to say that you need to specify a linking set of expressions that you're allowed to link with in order to state the theorem. I've put a little fee here, which is a way of building in conditions on the ET prime that need to be satisfied. Only then I will consider that this is in my linking set. And I can talk about that later. Next thing, you need to somehow say, okay, ET linked with ET prime will be equivalent to what at the source level? Well, it's ES linked with something that is drawn from what I'll call our source target linking medium. For Pilsner, this S hat language was just the source language S. For the multi-language approach, it was the multi-language. Okay, so you need to somehow specify what is this gray box going to come from. Then you need to specify a lift relation that says how you would take an ET prime that someone gave you and relate it or lift it to this, this gray box, okay? A way of specifying the relationship. For Pilsner, this lift relation would just be the cross-language relation or the Pils relation. For the multi-language approach, it would be the lift relation would put an ST boundary around this target component ET, right? So different ways of specifying the lift relation in different formalisms. And then of course you need to specify what is target level linking and here you need to specify what is source and whatever you chose your source target linking medium to be, what is linking for that. So all of these things are you know, let's assume that we have them. Then here's the CCC theorem that we want, and I'll just try to read it out in the right order. You want to show that there exists, given a compiler, there exists a lift relation such that for any source component ES, if you compile it to a target component ET, and then you link with some ET prime drawn from your specified linking set, then the lift of that ET prime, when linked with ES, will behave the same, okay? And then there's a technical requirement on the lift relation that just means lift is inverse of compile on the compiler's output, technical condition. I'll just refer you to the paper for that. Okay, so this is a bit technical, but what this is intended to be is a framework so that you can plug in different, you know, your choice of lift relation, your choice of what S hat should be, what is this gray box, what language technically should it be drawn from, and so on, in order to verify your compiler. And what basically falls out is, and of course, whole programming separate compilation theorems should follow, do follow from this CCC theorem. And basically what falls out is that all of the results that I've shown you throughout this talk, they can actually, you can specify each one of these, you know, lift and S hat and so on, and linking set for each one of those results and start to compare them. Okay, and you can show that each one of those formalisms are in fact applying our CCC theorem when plugged in with appropriate definitions from those formalisms. So it gives you a unifying sort of framework for the space, hopefully. That's just more on that. I'll refer you to the paper for more. So just to sum up over time. So I just want to say that, you know, Comcert was an amazing result. It started a renaissance in compiler verification, and it's led to major advances in mechanized proof. The next chapter, though, is about compositional compiler correctness, right? In order to verify our compilers and get compiler correctness theorems that match how we actually use these compilers, and I claim that we use them to link with code. We almost never write code that we will not be linked with anything, right? We need to figure out how to do compositional compiler correctness, right? But what I've shown you is that source-independent linking and vertical compositionality are at odds, and there's really a need for newer proof architectures here. And to study this problem more deeply, there are some very interesting semantic questions here and engineering questions. And I just sort of like to leave this by saying that, you know, all of this work, ideally this should apply to a world in which we build multi-language software, because we do that an awful lot these days. All right, and what we really want is, you know, I've sort of categorized different languages. We want verified compilers for a multi-language world, right? C, C++ are not so safe languages. ML, Haskell, Java, you know, statically type safe languages. Rust I've put in a different category because it has this notion of ownership and borrowing. What happens when we compile this to the same target and link them together? These languages have very different source level invariants and guarantees. Mixing unsafe code with safe code from ML or Rust, you know, what does it do? It obviously violates, you know, we don't want it to violate guarantees that we might have in our safe languages. So how do we tackle that? So what I'd like to say is that there's an enormous amount of research to be done on safe FFIs between these categories of languages and getting a better handle on that. And that problem is incredibly related to this question of how do we do compositional compiler correctness while allowing linking with code that comes from different languages, right? Okay. this was just an attempt to say that somehow your target language needs to talk about safe interoperability between these different categories of languages. And we need to design safe FFIs. All right, so I'm just going to leave you with a pointer to this one additional resource besides the ICFP 19 paper. I have a bunch of lectures on YouTube where I talked about some of these issues back in 2017, which you might find useful. So thank you.
Awesome. Thanks, Amal. Again, you'll have to use your imagination and imagine my applause being amplified hundreds of times over. That was a super great talk, and we have a whole bunch of questions to answer on the Slido if you're down for a couple of them. One of them is really relevant to a couple of slides ago, where you were talking about, like, for example, linking C with Rust. Priya asked, what would be needed in order to use programs, libraries, and typed languages with those in untyped languages, or vice versa? What kinds of assembly language features do you have to add things to the assembly? And if you don't mind my embellishing a little bit, beyond just like C and Rust, what about dynamic languages like, maybe Python and Rust? Who knows?
Absolutely. So dynamic languages fit in there very much. So here's what my group has been working on in fits and starts for the last several years, or at least thinking about in various ways. We are interested in designing some sort of a platform. This target level here is meant to indicate that, some sort of a platform. And right now we're working on doing this on top of WebAssembly that allows you to have rich type features. So basically what we want to do is we want to do type preserving compilation from statically typed languages like ML, and also from languages like Rust. Of course, if you're doing type preserving compilation from Rust into a target language, and again, let's just say WebAssembly, you need some notion of capabilities and ownership and borrowing built into that target language. If I'm doing type preserving compilation from ML, Haskell, Java, these are roughly all in the same category. You need, some sort of, you need a type system, polymorphism for closures, et cetera. This is all going back to the typed assembly language work. Features from that in order to need to be present in this target substrate, so that we can then start to think about, what happens if I take a Rust object represented using some sort of capability and pass it over to ML land? Well, what I think would be interesting to do is, of course, the way I'm talking about this, you can imagine that I'm sort of hinting at some very richly typed, but also gradually typed, because I want to mix untyped code in here, right? Target language in which you can do all the work of ensuring safety, right? And I think that is exactly the kind of thing we ought to aim for. We will not be able to have a universal compiler target that will accommodate absolutely everything in the world. Such a thing does not exist. Such efforts have been made before. But I think there's been so much work in the last decade or so on this idea of multi-languages, mixing of typed and untyped code, more precisely and less precisely typed code, that we really do have the techniques and the technology to start to design this well. And why am I focusing on designing this well? Because I think that if one set of researchers designs this well, then a whole lot of researchers who compile to that substrate will just sort of benefit from having, from the work already having been done. It'll be easier for them to think about, what is my safe FFI between Java and Rust? How do I prove the soundness of that FFI? That's another thing that we are working on right now. Actually, we have a semantic soundness technique that says, what do you do when you implement an FFI? You actually go into your target language and you are implementing some sort of conversion functions between the types or data in one language and the types and data of the other, right? But how do you know that that's correct? And that's a sort of semantic question, and you can use techniques in order to verify soundness of FFIs.
Awesome. Great plug for WebAssembly in there as being an important technology here. Another question that I think is super interesting on here is if there's, asked by Matt, who asks if there are overlaps with other techniques that might be able to, for example, to say something about debugging information. That is, it like that compiler optimizations, for example, are correct and preserve debugging information through, that you find in DORF, for example, executable formats.
So that's not something I've thought an awful lot about. My first reaction would be that preserving debugging information it kind of amounts to, basically, thinking you need to make sure you're sort of trying to give a semantics to that debugging information as it's made available in the target, right? And you need to be able to relate it to what's happening in the source. So I don't think anyone's done that. as part of compiler verification. Seems like a very interesting thing.
It struck me as interesting too, specifically because it has to talk about the semantics of the target language and the source language at the same time.
Yes, exactly. And so doing this on top of the kinds of relations that we're already setting up perhaps between source and target would be really interesting to study, because you already have this rich framework there and you just need to augment it with something.
Totally, yeah. Okay, here's another intriguing question. It's the most upvoted one right now from Anonymous, who says, do you see applications of verified compiler teaks to an environment like Graal Truffle, which allows running different languages on the JVM?
Graal Truffle is amazing work. It's really great. But I haven't thought about how to integrate these ideas of safe interoperability in there. That's my sort of, I guess, top level answer. In an ideal world, that I wish for is integrating, all the useful work that they've done in terms of implementation of these things, and having VMs where you have a lot of rich type information so that you can actually think about safe interoperability, whether or not you're getting safe interoperability between the original source languages. So that's almost a non-answer, I apologize. But
I think that makes sense. Another thing that came to mind when I was reading that question is that it adds another dimension, which is just-in-time compilation, that makes all this harder and more interesting.
Yeah, so I don't know. I've thought a bit about just-in-time compilation, but not so much integrating it into the work that we're doing right now. The way that I think about it right now is that when you do this kind of, if you're interested in language interoperability and compiler verification at the same time, I tend to say, all right, you want to think about different languages being compiled to a single substrate, and perhaps for starters, you make an assumption that this is the substrate in which all of your linking will happen. Maybe you'll have whole programs. And so if I were then doing JIT compilation after that, which is a logical assumption for JIT, for JITting, then I think that we could very much, because now we're in a whole program space again, we can think about correctness of JITs that go from this substrate down to a target, because now we're just dealing with whole program compiler correctness, right? So we're in an easier space. We don't have to worry about unknown code that we link with anymore. So I think that ought to be tackled below the level of your unifying substrate for linking.
That's a really great point. That is one luxury that JITs have, is they get to make at least a temporary closed world assumption.
Yes, precisely. Yeah.
Cool. All right, I have one slightly more unconventional question for you. Priya says, I really like the visualizations of theorems and systems that you use. Do you think the PL community should rely more on diagrams to convey complex concepts?
Absolutely.
I agree.
I think my diagrams sort of come from how would I draw this on the board if I were actually lecturing on a board, because I tend to do that a lot. So that's actually a good way of saying it to someone. How would you show it to someone on a board if you were just sketching it out for them, and maybe use that as inspiration for how you want to do it in your slides. Right.
Yes. Good point. Cool. Okay, we're over time, so there's a couple more questions in here that I'll put into the Slack for further discussion. But I really appreciate the talk, Amal. That was super great. I'm going to clap one more time, and everyone can clap with, in their own rooms if you also move.
Thanks for having me. This was great.
Awesome. Thanks, Amal, and thanks to Mike. PLMW is going to be taking an hour-long break, during which some of us will be hanging out in the disco rooms. So please feel free to join up with us there. Otherwise, we'll be back for another session in about 1 hour. Thanks, everybody.
Thanks.
All right, I'm going to share this test pattern thing for a while. That was really great, Amal. Thank you for the talk.
Thank you. Yeah, sorry, I went over. I think I said too much on various slides. So.
I thought that actually worked totally fine. We were still within the hour limit, and it was still time for questions. So you can count that as a success, I think.
All right, great. See you later then, Adrian. I'm gonna log out.
Thanks, Anu.
Hello.
Thanks for all your help making sure this worked. Melinda's joining. Okay, great, good.
Very hard work. I'm leaving this Zoom meeting then.
Wait, sorry, what was that?
Can I leave this Zoom meeting?
Yeah, I think you're all good. Thank you so much for your help.
No worries.
Thank you so much for your help.
No worries.
Yo,
How's it going?
it's going all right.
It's going
Get
all
it.
right.
Get a snack, I guess, here.
Hang on, I think I might
Get a snack, I guess.
go on the YouTube. Let's
Great.
find out. It occurs to me that whatever we say right now will be broadcast on YouTube, so maybe.
Exactly. And hopefully edit it out later. Okay, I'm going to put myself on mute and go try to eat something. Great. It was a
Hey guys,
hey Gene.
how's it going?
It's pretty good. I'm trying to cook lunch at the same time as admit people from the waiting room. Very exciting. Hi Eva.
Hey, now.
Hi Chandra.
Hi. I just was telling Milian that it required a password, but it doesn't. So.
Oh, okay. Got it. Well, here we are. I'm going to try making Milland the host so that I can continue making lunch. Well, Milland, you press admit from waiting room.
All right, I can do that.
Yeah, sweet. Good.
Hey, everybody.
Hi.
Hello.
It's great to see everybody. So.
Yeah.
Yeah, good to see you guys too. How's everyone doing?
Surviving.
Not bad. Yeah.
Good.
How are things in California, Gene?
Pretty good. Very busy, but yeah, I feel like some people are like, this is such a chill time in my life. I'm just taking it slower. And I'm like, what? Well, I think that also, I don't know, like cooking all my meals takes a really long time. And like, there are like many things I could outsource to the outside world before, but now I have to do them all myself.
That's right. We're all insourcing. I also feel like, and Ava, you might agree with this, that there's a strong correlation between people talking about how chill this particular time in their life is and whether or not they have small children.
Yeah, well, I don't have small children, but I just feel like I don't know where, like, I guess like I developed all these side projects, but I don't know. I feel like I'm very busy. Even when I dropped my side projects, I was very busy. So, yeah. But how old are your kids, Milind?
Mine are 2 and 4.
Oh my gosh, yeah, that's
So
quite a handful. That would not be a chill time.
Yeah, well, so they are actually back in daycare as of last week.
Oh wow!
And so that has really dramatically, reduced my stress level.
What kind of precautions is the daycare taking? Is it
so the main precautions they're taking are so obviously all the staff wear masks. You can't really get 2 and 4-year-olds to wear masks. They don't let any parents into the daycare. So parents, we actually pick up and drop off our kids outside.
Wow!
So we don't go into the building.
Wow.
So that's the main, and then the daycare has reduced hours so they can do more thorough cleaning.
That's nuts, but that's great that that is available again.
Yeah, it was we sort of went through a big process of like risk assessment and figuring out sort of how much risk we were willing to tolerate in terms of sending the kids back to daycare. The main thing that tipped it for us was that it's not actually clear that anything's going to be better a month from now or 2 months from now.
Yeah, so that's the thing.
What are we like? Either we commit to keeping them out of daycare for the next 8 months or something.
Yeah, that's a lot.
Oh,
sorry. Oh, I think this is like part of the live stream right now. If you guys don't mind all the conversation being live streamed.
Yeah, I'm actually I'm quite happy to talk about the difficulties of childcare on a live stream, because I feel like that's actually a useful thing for people to hear about.
Yeah,
but we will also,
that is true.
when we make the stream, when we sort of like leave the final video, we'll cut this part out.
Yeah, I feel like I just come off like a jerk. I'm like, I have no responsibilities, but somehow my life is also hard.
So by the way, let me, in case you guys have not met, let me introduce all of you to Irene. Irene is going to be our student volunteer. She's going to help. She's going to monitor the live stream, make sure that everybody's sort of showing up correctly, audio's coming through correctly, things like that, and just generally help out with the technical stuff. Irene, let me also make you co-host.
Okay, cool.
And so the way that we'll do this, so thanks for joining a little bit early to chat about how we're going to make this all work. So we'll basically switch over to gallery view on Zoom when that time comes. And I guess, Irene, at that time, you'll probably want to turn your video off so that you're not in the, unless you want to be visible in the panel also.
Oh, yeah.
Entirely up to you. So then basically all the questions are going to come in over Slido. and there's an opportunity there for, if you haven't used Slido before, for people to upvote questions, to basically say promote questions, and I'll basically moderate those questions and pass them on to you guys, either if they're directed at particular people, to the particular people, or sort of open it up to everybody. And I thought, I think as I mentioned in the email, I thought that the way we could start this is by everybody introducing themselves and just talking a little bit about your path through grad school. And we'll do, and then we'll get questions from there. And I have a couple of questions in mind in case people are shy about asking questions on Slido.
And is there like I guess like an underlying theme of the panel? Like, is it we want to
the
tell
underlying
people...
theme of the panel is I mean, the title is basically surviving grad school. And I think that the story that I often tell people myself about surviving grad school is that, and this has actually come up a couple of times in other questions and some of the other panel, is that it's really easy for us to look at sort of our peers or people we know and make it seem, and it makes it seem like everybody has a really easy time in grad school, and that like, but there's a lot of ups and downs in grad school that are tricky to navigate, and that it's I think worth people knowing that those ups and downs exist, but also understanding sort of how people dealt with sort of managing their lives in grad school and managing.
That's helpful.
Managing the various challenges that go into grad school.
Cool. So I guess in the intro we can like hint at that.
Yeah, that's what I was thinking.
Cool.
Fred, do you mind? Oh no, I was going to say, do you mind turning your camera on? But I realized I just didn't see you on there. I just wanted to make sure that was all working.
Hiding off the edge.
Yeah. So our panel, your panel will get started. You guys have some time to hang out. You can either just stay on the call muted if you want, just to avoid having any trouble reconnecting, or you can just reconnect closer to when the panel will start, which will be in, I guess, an hour and 20 minutes from now is when the panel officially starts. Any questions about logistics?
Yeah, how early do you want us to show up? Is it like awkward if we show up too early? What's the right time range?
So Emery's going to be giving a mentoring talk right beforehand. So it'll be in screen share view, which means that just like now, I think that what gets shown up on, like, audio will come through for everybody, but I think what actually gets shown on the live stream, and Irene, correct me if I'm wrong, is the screen that's being shared plus the inset of the person sharing their screen. So none of our videos, so even if you guys see our videos on Zoom right now, none of our videos are showing up on the live stream. So it's actually okay to just connect ahead of time. As long as you're staying muted, nobody will hear you.
Okay, cool. No, that's great.
Yeah, I just actually looked on the YouTube link to see what this looks like. And it's just whoever is speaking and the colored thing in between.
So as long as we're all muted, only Emery will show up in the inset.
Okay. So someday I'm going to take off this screen share, but like not yet, I guess.
No, we won't. Yeah.
Right. I think I will have to disconnect and reconnect later because the little one has to get food and hopefully go to bed.
Good luck with that. Well, I know that is a potentially unbounded process. So
yes, exactly. But I was just going to reconnect, mute it, and maybe without video, and then just switch it back on when it's time for the panel.
Yeah, I'll just mute and stop video.
Sounds good.
All right.
Goodbye, guys.
Then I'll see you later.
Just a bit.
Hi, is there anything else logistically that I can help out with right now?
I think at the moment, no. Once Emery connects, we'll make sure that his screen shows up. So I think the main thing is keeping an eye on the live stream itself to make sure that people are getting connected. Because I'll be watching Slido.
Okay. And you don't need any help with the Slido questions?
I don't think so, but we'll see how fast and furious the questions come in. So actually, if there's a question that I'm just missing because I'm sort of focused in on something, just ping me on Slack to let me know that.
Okay, will do. And then Should I also monitor the Slack channel messages in the meanwhile, or is that probably fine?
I think it's probably fine. I think so. My experience of how this has been going is that people kind of have side discussions on the Slack, but our questions are. If somebody asks a question on Slack that is not showing up on Slido, maybe it can be helpful to say, hey, this would be good to put on the Slido.
Okay, yeah, makes sense.
Right,
have
so
you been able to also look at any of the other PLDI talks simultaneously?
Well, why would you? I mean, the other PLDI talks are great, but why would you want to do anything other than watch PLMW?
Right. But it's the first time where you could be present in like multiple tracks at the same time. Yeah. Seems pretty difficult though to keep track of multiple things. You know how the social gather has been working for PLMW?
So I mean, I think the disco stuff has been working pretty well. We've had good turnout there. And that's been fun. It's a little bit like sort of sitting down at a random lunch table, which is the effect we were hoping for.
Yeah,
I was even eating lunch during the disco channel discussion to really bring that authenticity. So yeah, I think it's been going well. I haven't gotten up to play with Gather at PLDI yet, but I got to try it out a little bit before, and it's a pretty cool system.
Yeah.
All right, I'm gonna.
And then,
go ahead.
Okay, I'm also gonna mute my video and camera until the rest of the session, right? That should be good.
Yeah.
Yeah. Okay. Cool. Thanks.
All right. Amory, can you hear me?
Yes, I can hear you. How are you doing?
Pretty good. Let me do a couple things because there's some trucks outside my house. I'm going to put my headphones in. By the way, big
now it's still being broadcast on the YouTube live stream.
We are currently being broadcast on YouTube.
Although, sorry, I missed what you just said.
That's okay. All right, I'm trying to decide if I should put in one or two of these ear things.
Oh, sure. Okay, so let me turn off Adrian's screen share. Wait, how do I do this? Okay, so if you want to try sharing your screen, just so we make sure that we're seeing the right thing.
Okay.
And I will also connect on YouTube.
So I wanted to, well, we'll have to see what happens with animations and videos and all that crap. So let's see what happens. I'm a little scared given what I've seen. All right. We'll have to see what happens with.
Okay.
So yeah, so let's see. Is it still sharing?
Yes, so I see your screen. There we go.
Okay, and then let me see if this works. Did you go to the second page?
Yes.
Still, yes, okay, great. Cool, awesome. I was worried about that.
And then do you want me to ask questions during your talk as they come in on Slido, or would you prefer me to that I wait? Do you have particular points in the talk that you want to take questions?
That's a good question. No pun intended. So I have the Slido thing up on a separate monitor, so I can actually see I can see the questions.
Okay.
But I'm just trying to think in the presentation. So there's one long section of the talk that basically is like walking through, essentially like I made it more focused on PhD students. So I talked about my PhD work. So I was talking about, I talk about Horde, and then I come to an end and it moves on to the next thing, which is building real systems. But that's a lot of the way into the talk. And then the rest of the sections are much shorter.
Okay.
So I would say if there's going to be a question, it's unlikely there's going to be a question, I would say, super early. But I mean, if there's a question, I mean, I would prefer to go through to the end of the what I'll call the scratch and itch session.
Okay. Yeah, that sounds great.
Okay.
We can totally do that.
Okay. Sounds great.
Yeah, this looks like it should show up pretty well.
Good. All right. Fingers crossed. Do I have enough time to get coffee?
Yeah, I'm actually going to go get something to drink too.
Okay, super. All right, I'll be right back.
You ready, Emery?
Sure. Let's do it.
All right. Let's wait till it tips over. Okay. Hi, everybody, and welcome to the fourth and final session of PLMW for the year. So in this session, we have two things for you. We have a talk followed by a panel. The talk is going to be by Professor Emery Berger. He's a professor at UMass Amherst, where he's been for most of his, I think all of his faculty career, except for sabbaticals. And Emery, in case you're not familiar with his work, works at the intersection of programming languages and systems. And if you're not familiar with his work, you actually probably are, even though you don't realize it. If you've used a lot of modern operating systems, you have used the components in those systems. Many of the components in those systems have been inspired by the work that Emery has done. And so we were really excited to have him as part of our program to talk to all of us about how we can have impact with the work that we do in research. And I'm really looking forward to this talk, Emery.
All right, great. Thanks, Milan. Hi, everybody. Hope everybody's doing great out there. So today, like Milan said, I'm going to talk about how to have real world impact. The talk is broken up into 5 easy pieces. So I do want to say, I mean, this is my personal perspective. It's not like I have a magic formula. It's just that our research group, like, we always get asked, like, how do you have impact? How did you get adoption, and so on and so forth. So I sat down and thought about it and tried to come up with some common themes that seem to be effective ways of getting stuff actually adopted and out into the real world. And so that's what I'm going to talk about today. So some stuff I'm not going to talk about. When I talk about impact, I don't mean producing reams of papers. There's nothing wrong with publishing. We all love publishing papers, but at the end of the day, this is not how we want to go out. Having had published N papers for N large is not really something you put on your gravestone. It's not how you're going to be remembered. So another way that people often measure impact, if they're not just counting papers, is looking at citations. So this is my Google Scholar page. And there's a bunch of papers and there's citations, and people will be, oh, wow, there's, N citations and that's impact. But citations are also not real world impact, right? Well, to the extent that academia is the real world, I guess they are, but that's not the kind of impact I mean. I mean actual, impact on people's lives, not just on people's bibliometrics, right? So for example, some of the stuff that we've done, as Milan mentioned, has made its way into modern operating systems. And so we have a number of systems that have somehow been integrated into Mac OS or into Windows or into Linux, either directly or having inspired things that ended up getting in there. And so that's really what I mean by real world impact, right? Actually affecting the lives directly of millions of people. So during this talk, I'm going to talk about these 5 easy pieces. Some of them are easy, some of them are less easy, but that's the way it is. So the first one I'm going to talk about is scratching an itch, and I'll explain what all these terms mean. But we're going to scratch an itch. You build real systems, embed yourself, give great talks, and go to the mountain. So first I'm going to talk about scratching an itch. So what do I mean by scratching an itch? So everybody likes to have their itches scratched. Me too. It's always great to get scratched. But what I mean here really is not just like literally getting scratched, of course. I mean, there's something that is bugging you. And that thing that's bugging you is a problem that you are having, right? So if you're having this problem, attacking a problem that is, a problem that's directly affecting you, it's at least affecting one person, right? And you can probably extrapolate out that if the problem that you're having is something that is not super, super narrow, maybe it's affecting tons of people, right? So one of the problems that if anybody who's programmed in C and C++ knows, it's often difficult to get your programs to actually be correct, especially with respect to memory safety. right? You have a buffer overflow or a dangling pointer error or something like this, and it can be really tricky to track down and fix. And so the itch that we were scratching here was, how can I take this program, especially if it's a program I haven't written or it's crashing inside some component that I am not responsible for, and get it to work anyway. So we built this system called DieHard. And DieHard, it appeared in PLDI, and it won a most influential paper award, which was very gratifying. But the most gratifying of all is that it went out and had an influence directly on Windows 7 and subsequently on Windows 8. And so that's the kind of impact that that makes me especially happy. Another itch that we scratched was performance profilers. So if you ever try to make your program fast, sometimes you discover, well, after you get the very low-hanging fruit, like, oh, there's the one thing where it's spending a lot of its time, often it's very difficult to find more. And that's not really very helpful, right? So it kind of runs out of steam. And this is a personal thing. This is something that affected me when I was writing software, and it affected my students when we were writing software. And so we decided to attack this problem. So we scratched this itch by creating the system that we call Cause. Cause also was well received in the community, won a Best Paper Award at SOSP. But most gratifying of all is that it's a standard thing with modern Linux distros. So you can just apt install Cause, which is super cool. The one I'm going to spend the most time talking about today is one that came up during my PhD, since this is really a talk that's focused, being PLMW, focused on PhD students. This is something that happened to me while I was working on my PhD, and it wasn't what I was trying to do. This was not actually in my main line of research at all when I was working on this, when I encountered it. What I found was that the built-in memory allocators that come with standard operating systems didn't scale. And I'll talk more about what that means. But in short, if you had multiple threads, the programs wouldn't necessarily get much faster. The malloc turned out to be a problem. And so this led to the system called Horde. And this was is actually the first paper that I published. It last year won a most influential paper award, but as I'll talk about later, it also got rolled into some modern operating systems. And I think that this approach of scratching an itch, finding something that is affecting you, and then going from there and working on that problem is definitely a way of eventually having impact. All right, so let me tell you the story of Horde. So when I was a PhD student, my first advisor was named Bobby Blumoff. He had just finished up his PhD at MIT, working on a parallel programming language called Silk. And he moved to UT Austin, which is where I was. And the idea was, well, all right, so Silk is a modification of C. Let's make something that's really more like a library that you could use in C++, because libraries are more likely to get adopted than a whole new language, which I think is mostly true. This logo, by the way, is by my brother, Doug Berger. If you know anything about computer architecture, there's famous Doug Berger. I guess my brother is kind of famous, but in a different circle. Anyway, it's been a source of a lot of confusion over the years. Be that as it may, one of the things that Bobby naturally wanted to do as we were working on the implementation of Hood was to come up with benchmarks that we could use to evaluate it and to show that it was really good. And so he said, hey, why don't you rewrite a bunch of Silk benchmarks into Hood? And this struck me as a terrible thing to do. I didn't want to do it at all. It seemed laborious and boring. So I basically was like, nah, I have a better idea. Here was my better idea. I'll just write a parallelizing compiler. It seemed like an easier thing to do at the time. Certainly more interesting. That part is true. So what on earth was I thinking? So, well, it's a good question. What I was thinking was, I was at UT Austin, and at UT Austin, there was this theorem prover at the time, which used to be known as the Boyer-Moore theorem prover, and it's now known as ACL2. And it has one thing that makes it very appealing from the perspective of doing a parallelizing compiler, which is that it is a pure functional Lisp. And in particular, it doesn't have this nasty thing about eval. So my idea was very simple: take pure functional Lisp, step 2 something, step 3 profit, where we'd have instant benchmarks, and my step 2 was write a parallelizing compiler. Now, in the limit, this is really an incredibly borderline impossible thing to do for most programming languages, but in this context, it kind of made sense. So I wrote a compiler that basically could compile pure Lisp to C++. It wasn't that hard. Anyway, it was hard enough. It wasn't that hard. It certainly was more engaging than rewriting the benchmarks. Anyway, there was a bunch of code out there in ACL2. I forgot to mention this. There's all this ACL2 code. If I had the compiler, then magically, if it was using Hood, then I could just run all that code, and then I wouldn't have to rewrite anything. So that was my idea. So be that as it may, the idea was you go ahead and you take your pure Lisp, compile it to C++. The compiler generated code that produced a thread for every let clause, because those are conceptually independent. And then I wrote a ref counting GC. So off to the races, or to the benchmarks. So here's what happened. I took some code, and this is the way all the graphs ended up looking. This is a pretty classic graph that you would see for parallelism. On the x-axis, you have the number of CPUs from 1 to 8. We had an 8-processor beast at the time. And then perfect speed up, of course, would be a linear speed up, right? The more CPUs you have, the faster things get. And unfortunately, this is what actually happened. So in fact, as you added CPUs, as you added threads, things got slower and slower and just kind of dove down into the x-axis, which is certainly not good, because our goal was high performance. And you know, it took me a while to figure out what on earth was going on, but you'll be unsurprised to learn that the problem turned out to be the memory allocator. So we were actually, and again, I had no interest in working on memory allocation at the time at all. So I just went and looked around, and I was like, well, what is the off-the-shelf replacement that I can use? Because this is clearly terrible. And I was shocked to discover that the past work that had been done in this area really wasn't that great. So the problem that we had in the standard memory allocator was that it had one big lock. And so one big lock makes it impossible for multiple threads to actually work in concert. So that clearly was a problem. But then it turned out that, you know, that managing these things, well, it's complicated to manage them the right way, but they had other problems. So here, you of course have a picture of memory allocation. You have these two kids who are fighting over something, and the thing they're fighting over here is a cache line. So it turned out that these memory allocators, even if they had multiple threads, they would routinely parcel out memory that happened to be on the same cache line. And so if this thread had a piece, and then this thread had a piece, and they're both using that piece, it's as if they were locking all the time, because the cache line was constantly getting invalidated. And so that was a disaster for performance. And then they had this other problem. All of them suffered from one of these problems or more, where if one of the threads was allocating and then it freed it, it might go to the other thread, and the other thread would store it. And then the first thread again could allocate some memory, and it could free it to the other thread, and so on and so forth. And those threads, like in some of these heap organizations, they would never recycle any memory. So the first one would constantly be getting memory from the system. The second one would just be piling up and piling up. And you could write a program, and I did, that would quickly exhaust all available memory. And you knew this happened because all of a sudden the computer would freeze and become totally unresponsive for seconds or even minutes. And then eventually would, well, basically was dumping core because it exhausted all memory. So this is clearly no good. So let me briefly talk about the solution that we came up with. I'm not going to go into much technical detail, just to kind of like animation and diagrams. The first idea was, let's get memory in these big chunks that we called super blocks. The super blocks would be managed essentially exclusively by each CPU. So every CPU could allocate and free from its own super blocks. And then it turns out that by doing this, by grabbing big chunks of memory, which was the sort of idea of hoarding, we would avoid a lot of locking. But more crucially, we'd avoid this problem of false sharing, the toddlers fighting over the ice cream cone, because it would not be possible for one thread to allocate memory to get a piece, and then another thread would get another piece, and so on. Each thread would have its own pieces, so they'd get their own cache lines. Then, as allocation proceeds, these objects are consumed, and now they're getting freed. So the black means they're getting freed. And of course, this problem of all the memory accumulating on one thread, that's not what we want to have happen. So as these blocks become emptier and emptier, we would move them to a global heap, and the global heap makes it available for reuse. So you never end up with a situation of the giant tire. And we have a discipline that does this, that provably avoids locking in most common cases, and prevents this problem that we called blow up. So we went and we took Horde and we plugged it back into these benchmarks, and instead of it looking like this, we ended up with performance like this, which obviously was an improvement. So then before we actually had a chance to really build the system and get it out the door as a paper, Bobby, well, there was an era at the time that Bobby was a faculty member back in the day. It was called the .com era, the .com boom, and there was this startup that still exists called Akamai. And so, during the .com era, there were all of these startups, and people were attracted by all of the deep and super interesting technical challenges that would naturally pull people from academia to startups, much as today. So Bobby left, and it turned out by great luck at that moment, Catherine McKinley had moved to UT Austin to do a sabbatical, and she eventually moved to UT. And so Catherine became my advisor starting in 1999. And you'll see there's no end date because, as Catherine says, advisor is forever. So she is my advisor till I die. So we wrote a paper. So you can see our names on there. And it, again, went to ASPLOS, and it got this most influential paper award, which was great. But more gratifyingly is what came afterwards. All right, so let's get back to the scratching niche. So I had an itch to scratch. Malloc doesn't scale. Again, it's not what I was working on. It wasn't my goal here at all, but I discovered this problem, and I realized this is probably a problem for a lot of people. And it turned out it was a problem for a lot of people. And if you think about it, there's going to be a lot of problems that you're going to encounter that are issues that are really going to affect a lot of people. And if they're affecting you and you kind of think, it's just running multi-threaded code, surely multi-threaded code is going to run into this problem at some point. Yeah, you're probably not the first person to discover this issue. All right, so we built this system called Horde. We put it out there. It got adopted by a bunch of companies, but perhaps the most gratifying part is that it ended up, the algorithms in Horde ended up going straight into Mac OS. So this is actually from Apple's open source implementation of their memory allocator, and kind of amazingly, they actually cite us. I mean, they cite the SIG plan notices. What are you going to do? But it's still okay. So yeah, so really, if you're using a Mac, there's sort of like the canonical PowerBook, MacBook. This is there's me inside. All right, I'm along with my collaborators. Okay, great. So that's scratching an itch. So the next easy piece is building a real system. Oh, I forgot, if there are any questions, Milland, this would be a good time to take a pause.
So just as a reminder to folks, you can submit your questions via Slido. Our code here is PLMW4. I did have a question that just for my own education, and it might be better to take this question at the end of the talk, but your anecdote here really, I think, illustrates that, one way that people have impact, I think especially today, is that they sort of move back and forth between academia and industry. And so Bobby Blumoff going to Akamai is I think a great example of that. It sounds like you have a perspective on having impact from academia that's maybe a little bit different than I'm going to go over to Amazon for a while, or I'm going to go over to Google for a while, or maybe even permanently. Can you maybe talk a little bit about those two different approaches?
Yeah, so I'm actually going to talk about that later in the talk, somewhat briefly. So maybe when I get there, it'll be obvious when I get there, and then I'll expound on that, and maybe you can follow up.
Sounds great.
Okay, cool. All right, so building real systems. So so this is a picture of an aqueduct in Tarragona. It's got this name. It's Las Ferreras, or Pont del Diable, which is the Devil's Bridge. And this bridge was built probably during the reign of Augustus. So about 2,000 years ago. That is as real gets. It's, built of stone. It's, Roman engineering. This thing has lasted for thousands of years. It delivered water from 15 kilometers away. So this is clearly a real system, something we should all sort of aspire to. It's hard to imagine software living for thousands of years, but something certainly real. Unfortunately, a lot of systems that people build and certainly that are discussed in the literature are kind of more like this sort of bridge. So this is a pretty bad bridge. It's obviously a toy. You can tell that it's a toy not just because it looks like a toy, but because the people who are on the bridge have to wear life preservers. And when you're on a real bridge, you don't have to wear a life preserver because the chance of the bridge collapsing, you hope, is pretty slender. And unfortunately, a lot of software, especially research software that people put together, I think there are aspects of the culture that make it so that it kind of nudges people to produce toys instead of trying to produce real systems. It's obviously harder to produce real systems, but I argue that this is the way that you will have lasting impact. So let me give you an example of one of these nudges, which I think is unfortunate. So when people work on things that have to do with performance, and there's lots and lots of different areas where this happens, there's these benchmarks. There's a famous set of benchmark suites called SPEC, and it's from the Standard Performance Evaluation Corporation. And it's nominally used by vendors. So for example, when Dell wants to advertise that it has some system, they run this benchmark suite. But we use these benchmarks. So these benchmarks are things that we actually evaluate our systems on. And it's pretty standard for us to have papers that are that exclusively rely on these benchmarks. So I want to dive in and talk about a couple of these benchmarks for just a second. So let's look at this first one. It's 600.perlbench_s. So you might say, oh, Perl bench. Well, yeah, it's Perl. So it's a cut down version of Perl. Remember the last time you used Perl, that awesome programming language? That's a real thing. I mean, it was a real thing at one time. Fine. It's a cut down version of Perl. Okay, that's a little sketchy, but fine. What's it running? Well, it's running Spam Assassin. What is Spam Assassin? Spam Assassin classifies mail, so email, and decides whether the email is spam or not. And this particular version of Spam Assassin they're using is patched basically to avoid doing I/O, which is pretty sketchy because the whole point of doing it's email, right? Email is not necessarily compute centric. It's certainly doing I/O. And they've also disabled Bayesian filtering, which is a major part of what spam detectors do. Great. All right. So that's Perl bench. And you might think maybe I'm picking on one and this is an outlier. It is the first one. Well, let's move on to the second one. So what's the second one? The second one is a version of GCC. GCC is a compiler that probably none of you use anymore because it's been supplanted by LLVM or Clang. But it's a version from 2010. Awesome. And its workload is literally compiling itself, as one does. So these are pretty odd benchmarks. Now, what you see is you'll see programs, and obviously there's other benchmark suites, and there are colleagues of mine who put together benchmark suites that are better, and yet they're often not kind of real. And then there are cases where people will build their systems, and the systems don't even run all of those benchmarks. So really what's happening is you've got these racers, right? You building your systems and you're headed towards the paper deadline. And once you get across the paper deadline, you're done. And as long as you can push that thing across the deadline, and I'm not calling out anybody in particular, right? I'm saying that it's just it's a nudge, right? Like, where our goal is to produce papers. Nominally, you produce a paper, it's out by the deadline, and you did enough implementation to do kind of the bare minimum to get the paper accepted. So this is unfortunate, and it's unfortunate in many, many regards. So let me give a few examples. So first, there's no reason we need to restrict ourselves in a lot of cases to working on these toy random benchmarks or very, very small programs. I've seen some papers that work on benchmarks that are handfuls of lines of code. There's so much code available there's so many real systems that we can use. I mean, the system I'm using right now is Keynote. And I only just learned, by the way, that the logo for Keynote has the word Keynote on it, which is kind of an Apple UI fail. But anyway, there's browsers, right? So Chrome and Firefox. There's other sort of productivity applications like Office. There's server applications galore. These things are generally open source, so you can get the source code. They're big, they're real workloads. People are really using them. They're not just running GCC on GCC, right? So why do I insist that this is something to do? You know, I personally don't find it believable or credible if I see a system and the system is advertised to run on code that is, 100 lines, right? And even spec is kind of thin, right? And it doesn't really tell you what the real world impact is going to be, right? Like running Spam Assassin with IO turned off is not running Spam Assassin. So how does it behave in the real world? Well, you kind of don't know. And building a real system that can run on real stuff is going to tell you, right? Reality is the ultimate test. Okay, so that's part of building a system, evaluating on something real, going above and beyond maybe the low bar that is set by some communities. But another part, which is really not so much about the evaluation, but about the culture of building systems, is using this thing called GitHub. And I'm not pimping for GitHub specifically, but some open source repository. And not just using GitHub because, and I'm going to use GitHub again as a proxy for all of these things, not just using it because it's helpful and convenient, but also because when you create your repository for your research, what you should do is you should make it public, all right? I understand the temptation to keep things private, but developing something out in the open is first a way of being very honest about whatever you're doing. You're probably not going to put too many comments in that say this doesn't work or a giant hack here, although you never know. But it also encourages you to build something for real, because you may have this kind of psychological impression that people may actually see it. And if they actually may see it, maybe you won't cut a corner and maybe you won't do something that is not really going to work. You'll just be more careful. And it will make it easier when you're done to make it public because it's already public. All right. Now, I have allowed students to, on very rare occasions, to make something private with the understanding that the moment we submit a paper, it's made public. I personally think it's just fine to go ahead and work on these things publicly. If you have something that's real and that is out there, as I will explain momentarily, it can actually make your research better, right? So it's not like, oh my God, somebody's going to scoop me. First, it's very unlikely. Second, you'll probably end up learning something and improve the research in the process, all right? So I encourage you strongly to make these things public. Having your work on GitHub, even if you didn't do it initially publicly, and you eventually made it public, is a huge way to have impact. So one thing that people sometimes do, less so in our community, thankfully these days, is I'm not going to publish my code and I'll keep it to myself, and you can mail me if you want a copy or something. This is crazy. So we've built all of these systems. So this is me and my research group, and you can see there's this metric on GitHub called stars, and the use that we've gotten out of these things and the adoption that we've gotten has really been driven in a lot of ways, not just because we're producing real systems, but also because they're publicly available. And people have contributed to these projects, like we ported to this, or there was this problem here, and we discovered a bug. So there's all kinds of things that really help. And of course, having the thing already public and already ready to go makes it a hell of a lot easier when it comes to artifact evaluation. And I will say this, I think that these badges, these adorable, pretty little badges, which are, and I love artifact evaluation. I'm thrilled that it's become a standard thing in our community and is spreading to other communities and really got adopted by the ACM as a whole through the efforts of folks like Jan Vitek and Shrem Krishnamurthy and Matthias Hauswirth. And I'm sure I'm not mentioning others who've done so much. These artifacts are also kind of a badge that means this is real. And when I see a paper and it has artifacts like this, I know that I can trust that this paper really does what it says it does. And when I don't see them, I'm worried, and I'm not the only one. Okay, so let me give you just a brief anecdote about where publicly pushing stuff out to the world has made a difference. It's really helped almost every software project we've had. The fact is that the real world tells you things about your research that you hadn't thought of. So this happened recently. We have this new profiler for Python. I'm not going to explain any of the details, but it got picked up on Hacker News, which is generally a swamp, I will say. GitHub pull requests are usually wonderful, but Hacker News maybe not so much. But nonetheless, it's because it was out on GitHub that it got picked up, and we got this comment. And I'm not going to get into details about the comment, but basically there was a problem with the way that the profiler worked that we had not anticipated. And it was like, okay, good point. And so we ended up changing what we were doing with scaling and came up with a new research contribution. And just kind of amazingly, sometimes nice things happen on the internet, and everybody was kind of as amazed as we were. But be that as it may, the point is that getting stuff out there is a way of actually getting, you get a user and the user is like, hey, what about this? And you're like, oh, that's a hard problem. That's an interesting problem. Let's come up with a way of fixing this problem. So it's kind of like, not only are you getting your stuff out there and it's potentially getting used, but it's a virtuous cycle. It improves the research. Okay, so the next piece is
Emory, let me pause you here and
oh, sure.
Get a couple of questions. I messed up the way moderation was working on Slido, so there's some questions from the previous part also that hadn't made its way out. So let me start with that. Which I'm going to group together a couple of different questions that are related to scratching an itch, which is sort of, there's two parts to it. One is people either are having trouble coming up with itches, coming up with problems, or at least are worried that the problems that they're coming up with are maybe only important to them and not things that are important to the rest of the community. And so how would you go about both finding itches that are irritating you as well as irritating other people in the community?
Right. Okay. Good questions. So, I mean, the first one, if you're not encountering any problems, then good for you. I wish I were in your world. I don't know. I mean, I run into problems all the time. I mean, surely people are also running into the problems. I can't be the only one. But I'll give you an example that comes to mind. So James Bornholt, who recently graduated and is going to be joining UT Austin. He worked with Amina Torlak on synthesis stuff. And one of the problems they kept having was that sometimes synthesis would kind of just go wrong. It would just take forever. And it was like, oh, how do we debug these sort of problems? And he was just facing this problem because it's like, well, he was just trying to synthesize stuff. And every now and then it would go down some path where it was searching and it would be like exponential search. And this motivated him to create a profiler for doing synthesis. Now, this is not something that's going to have maybe, like my dad is not going to be using this debugger, right? But it's a problem that was definitely an itch that he wanted to scratch. And he realized that, this is, I mean, I don't know the full genesis of this, but I mean, from what James tells me, this is something that was just a problem that he kept running into. And it's like, how do we solve this problem? If I'm having this problem, other people are having this problem, and other people were having this problem. Maybe you don't know if other people are having the problem. There's easy, lightweight ways of finding this out, like Google, right? Stack Overflow. You can actually just go out and see, have people reported having these kinds of problems. And I'm thinking of things, because I see on Slido some questions about a more theoretical PL, certainly synthesis is practical, but it's kind of straddles both sides. I mean, I think of some of the stuff that Talia Ringer has been doing. All of these sorts of things are scratching an itch that people are having. It's not just their own itch, it's that they've recognized that there's some sort of problem, but I think if you encounter it and it's causing you pain, it's, we're not alone in this world. It's likely that it's affecting other people, but you can easily get confirmation and you can just talk to people. If you have problems and the problems are just your own problems, not every problem turns into a great research problem. But if you have one you have something that's been bugging you, that thing could be something that you should actually go and kind of like pull at and see if there's something there. I hope I answered. I answered at least part of your question.
Yeah, it was sort of a combination of multiple questions that were kind of all in the same vein of how do you find good problems? How do you find problems that other people are also going to think are important?
Yeah, I mean, this goes to the broad question of finding good research problems. I mean, this is part of the whole talk, really. So not building the system part, but building a system ends up uncovering other problems, which is really nice. Because once you get something out there and people are using it, then you're not the only one who's scratching an itch, right? Somebody else is like, hey, this isn't working for me. But then there are other ways of getting, of learning about problems and discovering problems that are things that affect other people, besides just like, talking to your friends and Googling around. So that's actually a good transition for this next part of the talk.
There's one more question I did want to ask. Sorry, I know that you have a a great segue there, but which is about your most recent section was about building real systems, and there's two questions that are basically the same question, which is that building real systems is long, hard work, and how do you balance spending the time of building real systems with doing the research and publishing the papers and all that stuff?
Yeah. So I mean, yes and no. So one of the things about getting stuff out there publicly is that sometimes people will do some work for you. So yes, it's definitely true that systems building takes time. I think that if you do the sort of like, I'm going to work on some giant system and then I'll eventually release it, like once the paper is out, that's actually pessimizing. That's doing things in the worst possible way. If you get stuff out earlier, you might actually get some users and some sort of traction where people will they'll fix bugs for you. They'll port things to different platforms for you. They'll uncover issues you hadn't thought of and you'll fix those things and it'll just make everything better. So I strongly encourage people to, certainly you have to be very thoughtful about building systems. You don't want to, spend a huge amount of time working on some system that, hopefully, I mean, God forbid you work on, like my nightmare is you work on some system and then, you work on it for years and years on end, God forbid again, and then you get scooped, right? Like somebody else was also working on a system. That's the worst possible situation. And I see somebody actually specifically ask this question about scooping your work if your repos are public. Those people will, if somebody tried to scoop work that you published in a repository, they will be in big trouble. It's going to be a problem for them. You getting it out there early is actually kind of a way of planting a flag, right? Like you have a date on that thing. It's kind of unequivocal. Now, obviously, this is, there's all this question of like peer reviewed and whatever, but in the world of systems, if there's an existing system out there, whether it's been peer reviewed or not, you often have to discuss it. And yeah, I think there's a very little risk of somebody scooping your work if you do something in systems, period. And putting it out there on GitHub is kind of a way of, like I said, of sort of marking that territory. And so I feel like I've forgotten one of the, or lost one of the questions here. Oh, systems building, about the time. Yeah, I mean, you have to be careful and thoughtful about these things, and you have to try to make sure that when you build systems, you build them in pieces where you're not spending a huge amount of time before you have checkpoints that are useful to get, pieces of your system out the door. But, if you build a system, if you're going to spend a lot of time building a system, first, you need to be careful about it. It's a good idea to get it out there early, but then, like build something useful, build something that people are going to use. That's way better than I spent, my research career building systems that nobody uses ever. So I think that there's like a combination of these things that all go together, but I do think that it's in your best interest to be working on systems that people are actually going to use and getting stuff out there so that they make your life easier. And of course, it leads to greater impact. Good?
Yeah, that was great.
Okay, fantastic. All right, so let me move on to embedding yourself. So the rest of the talk is pretty short, and we can move on to handling more questions. So for faculty members, embedding yourself usually means something like going on sabbatical or taking a leave and going somewhere. And this is something that Milan, you've mentioned, like going off to industry and then coming back. And I do think this is a really good thing to do. For PhD students, this comes down to internships, right? Now, clearly you could go and work for some time before going to graduate school. Stopping in the middle is probably not the best idea ever. So when I say the internship, I, of course, this immediately draws, Google comes to mind. Google is one example. There's lots of companies, of course, there's lots of opportunities to do internships. The key internships that we generally recommend that students do are at, the research organizations, right? So Google has a research arm. Microsoft, of course, has Microsoft Research. Facebook has Facebook Research, and so on. I don't think this is required. I mean, I think it's really good to do. And I mean, I interned at Microsoft. I sent many of my students to Microsoft and to Facebook and to IBM and other places, Intel as well. There's just going into industry period can be valuable, and even going to one of these companies, and especially as a junior PhD student, to just work in the environment and understand the problems that they're working on and see how they tackle them. Those things, it is the real world, right? And this connects you to the real world in a kind of convenient way. You go, you dive into the real world, you get to understand their problems and their perspectives, and then you come back. So having that, I go off and I get embedded into industry and then I come back, I think that is a way of staying in touch with the problems that people are having. Even if you have a problem that's not scratching your own itch, if you discover there's a problem that's pretty widespread, then this is something that can inform your research. And if it is a problem that's widespread and you solve it, you are very likely to have impact. All right, the fourth piece is giving great talks. So there was a very nice talk that Ranjit gave on this particular topic during PLMW. If you didn't see it, I know it's all recorded. There are other folks who've given wonderful talks on how to create great talks. Simon Peyton-Jones comes to mind. I highly recommend you go look out for Simon Peyton-Jones's talk on how to give a great talk. The one thing I'm going to talk about today very briefly is what I think every talk needs. And so I think every talk really needs to tell a story. So not every story is as engaging as this particular story, which is Princess Bride. It's your technical talk. But when you give a talk, you don't need to make it some sort of, here's my paper. Like the worst anti-pattern ever is giant PDF screenshot smacked into a slide. That is not what you should be doing. That's not telling a story. Telling a story is a whole other thing. Your goal is to convey the big ideas to people. And giving a talk in this way that's engaging, it has a lot of value. More people will read your paper if they like your talk. That's definitely true. Second, more people are just going to watch talks. Talks are way easier to absorb content. A good talk is a much faster way of getting content than reading a paper, right? It just takes a lot longer, and a talk can be really, really quick. And if you're creative with a talk, you can have kind of a lot of fun with the talk and engage people in the technical matter and in a way that they really get it. And then, or they have the right background to then go into the paper. Like they have the big picture, they have the story, and then they can go into the paper and they know where they're going. When I give talks, I do tend to rely on imagery. I have very little text. I take this maybe to an extreme. This is like the maximum level of text that you'll see on one of my slides. I don't think it's required, but I think that it's really a good idea to set your font size to something huge. First, it's going to help everybody see the talk. but second, it's going to limit the amount of text you can put on a slide, and that's really good. And it's really good because the paper is about text and the talk is not. The talk is about conveying ideas, and using diagrams and animation and imagery are often way better at conveying these technical ideas and getting people to understand the big picture than text. So think about that when you're designing your talks. And so I'll close with this going to the mountain. So this is Mount Rainier in Washington. It's a beautiful mountain, and sometimes it's even visible from Seattle. When I say go to the mountain here, there's the famous quote about Muhammad and God, right? If Muhammad cannot, if the mountain will not come to Muhammad, then Muhammad will go to the mountain, right? And so if you care about the real world and you care about real world problems, going to academic conferences is maybe not actually the best place to go, right? The mountains you should be considering are not your PLDI, watching double-decker buses go by on our screens, but this vast array of technical conferences. And they're everywhere. There's so many technical conferences out there. And they're dying for you to show up and talk about stuff. It's kind of amazing. And so some of the talks, some of them are very, very focused on particular languages or particular technologies. Some are broader. Strange Loop in particular tends to be especially broad, I would say. And it's, you literally say, here's the talk that I want to give. And then, they'll, if they like your proposal, which is very short, it's like an abstract, then you go give a talk. And then you're in front of all of these people, and then they talk to you about things, and they will give you ideas that you've not thought of, and you'll make connections, and they will be connected to problems that you had not considered. And you will understand their problems and learn about their perspective. So I really recommend this. These things exist pretty much everywhere. They exist not just in the US, but certainly in Europe and other places. They're often local. So there's like big ones that are like PyCon. There's a PyCon USA, but there was a PyCon in Budapest, and there's a PyCon in India, and so on. So there are local versions as well, and so they're pretty accessible and they're surprisingly welcoming. And I think the thing to understand is, as a PhD student, you're giving talks, you've given your talks, and so on. You've practiced these things. You have way more experience than almost any of the other speakers. So your talk is going to be amazing for them. And it's just a great way to reach people. So, so Strange Loop, I gave a talk at Strange Loop. My student Bobby gave a talk at Strange Loop. So this is some work that he did at PLDI, and he gave a talk at Strange Loop, and it, got to meet all of these people, and a lot of the, there was a lot of productive and interesting conversation. And so getting out there and talking with practitioners and talking with people who are trying to solve real world problems is definitely a way of having impact, right? So in conclusion, there's the 5 easy pieces I described, which are, of course, of varying levels of difficulty: scratching an itch, building real systems, embedding yourself, giving great talks, and going to the mountain. And that's it for my talk, and I'd be happy to take any other questions.
So let's do a virtual round of applause for Emery first. Maybe you can hear me clapping. I imagine you can't hear anybody else clapping. I can clap louder if you want. But there's a few great questions, some of which I thought were especially good to leave until the end of the talk. One of them, and you alluded to this question in one of the other answers that you gave, is a lot of your advice is definitely tied to people that are doing more systems-oriented research in PL, where you're building systems. Sure. And you're deploying those systems and getting users for those systems and stuff like that. How should one measure impact if you're on the more theoretical side of PL? How can you have real-world impact?
So, I mean, that's a big question. It's a good question. I mean, I think that, it's difficult to get adoption of like, here's a new language feature, and or I prove the soundness of this type theorem. I think that on the other hand, it is possible to do it. I've certainly seen people have found bugs in type systems and so on. I think that if you're going to have real world impact, like in PL, like the idea, nominally programming languages is about how we communicate with our with our computers, right? How we actually express the things that we want to say and have them implemented in some reasonably efficient way, and have them be hopefully correct and doing what we want them to do. There's a lot in industry these days. There's a lot of stuff, for example, about verification, right? Amazon is doing a lot of stuff with verification. I think that's happening increasingly. I think it's hard to answer this question broadly. If you're working on something that's extremely theoretical, then maybe quote unquote real world impact is not something that you can expect to have directly. On the other hand, I do think it's important to motivate the theoretical research you do by real world problems, right? So, if you're going to solve a problem, maybe it's not going, the theory that you're contributing is not going to have a direct impact, but at least you're hopefully solving the right kind of problem, right? Problems that, if you're working on, I don't know, Rust comes to mind. So, the work that was done by, Dan Grossman and Greg Morissette and Mike Hicks, and I know I'm missing a few people on Cyclone back in the day, was about solving these problems that were really like, how do we build systems that aren't, garbage collected, but are still safe? And that was a hard theoretical problem. It turned into, they built systems. I wouldn't say the systems had direct impact on the real world in terms of the system itself, but it inspired a line of work that led to Rust, right? And, ownership types. And I think that, ownership types actually date back to Jan Vitek. But anyway, so I think you can do theoretical work that is motivated by these real world problems, and you will have real world impact, or you can have real world impact. You're more likely to have real world impact in that way, but maybe it won't come right away.
Yeah,
I hope that answers the question reasonably.
I think it definitely does. This is a much narrower question now, but one that actually is also of interest to me because I am kind of in the same boat. So Mike, in his talk this morning, talked about a conversation that he had with Monica Lamb, where she said performance is dead and you shouldn't worry about performance. But obviously, a lot of your research is very motivated by performance and performance impacts and worrying about performance. Why? Let me phrase this more provocatively. Why don't you agree with Monica Lamb?
Yeah, so I first actually heard that from Dawson Engler at a PLDI. It was pretty funny, and I think that in that era they were right, because people were programming in let's say C or Java, and computers were getting faster themselves. And although it kind of petered out right around that time when Monica gave that advice, right? You remember how there was this great thing called Dennard scaling, and computers were just getting faster. It was awesome, and it kind of stopped like right after Monica said it. Like maybe that's exactly what happened. Is that Monica was like, performance is dead, and then it actually came back to life. So performance is a problem. I mean, I disagree with that assessment. I mean, times have changed. That's 16 years ago that she might have said that. And since that time, we're in a world where people use Python, for example, which degrades your performance by 4 orders of magnitude or more. People are coping with the fact that it's really hard to get performance out of these crazy systems with their complexity, like accelerators and so on. So that's a direct response to this question of performance. On the other hand, it's not the only research I do. And I didn't talk about any of this other stuff. I mean, I spent last year at Microsoft Research, and most of my time was spent focused on automatically finding bugs in spreadsheets, which has pretty much nothing to do with performance. And there's a lot of other projects that we have that have really nothing to do with performance. So I disagree that performance is dead, but I also don't focus exclusively on performance. Far from it. It's probably no more than a third of the work that I do. But I think it's a real problem. I think people, people really are actually acutely sensitive to performance. So if you dig up this talk that I gave at Strangely on performance matters, you'll learn more about it. But practically every update you get on an iPhone is improving performance or fixing a bug. People are very sensitive to performance and very sensible to bugs.
Yeah, I totally agree. There's a question that is not one of the more uploaded ones, but I thought was kind of an interesting one, especially given how much sort of very effective use of imagery and animation you make in your presentations. If a diagram is good enough to explain a topic and explain an idea, why isn't that diagram in the paper to begin with? Why is the paper so different?
Yeah, that's a good question. I mean, I actually really think diagrams should go into papers. You know, when I started off as a grad student, I was at UT. Dijkstra was at UT, and Dijkstra had this thing about he just hated diagrams and he hated examples and he hated like concrete things. And he's like, oh, they can mislead you, and you know the formalism never misleads you. And I'm like, you built up 30 years of intuition or 40 years of intuition, and then yes, it's fine to just like focus on the formalism, but you know, you come fresh to a topic or you come in as a reader of a paper. It's really useful to have examples. It's really useful to have diagrams. And so, you know, whoever asked that question, I 100% agree. Those diagrams should be in the paper. Now, it's hard to animate on a paper, right? So you have to, you know, unfortunately, that's the way things are still. We're still producing PDFs that are static. And so given that, you may have to design things somewhat differently. But I mean, if you look like the Horde paper has a diagram, kind of shitty diagram, to be honest. But like the mesh paper has the exact same diagram that we used in the talk. And I do think, in fact, giving a talk first before you have the paper ready is really helpful, because you'll come up with a visual way of talking about the thing. And then you can kind of, you know, make that serve two purposes. Just roll that diagram right into your paper.
All right, so I think we have time for maybe two more questions. So let me go with two of the more popular questions that are left. One is, so I'm just going to read the question, paraphrased a little bit. Suppose your system is already used by industry, and so it's already having real world impact. What more needs to be done before you can actually turn that into a top tier conference paper?
So, okay, so I'll respond in a joking way and then a serious way. So the joking way is that LeftPad was used by industry around the world. If you don't know about LeftPad, it's a node package that just added some spaces to the beginning of a string. And when the person removed it, it broke builds around the world, which is an interesting indictment of our current software culture in and of itself. But you know, just the fact that something is being used doesn't mean that it is like, that's not enough, right? Just the fact that like LeftPad, you can't be like, you know, PLDI 2021 LeftPad. So, you know, a top tier conference, people want to see big ideas. They want to see, you know, novel insights. They want to be convinced, you know, in the more systemsy side that things are real. So that helps a lot. And I will say this, with Horde, I actually released Horde before we had a paper, and then it got some users, and then I was able to put their experience in the paper. That definitely helps, right? There's no question. And the Horde paper has, you know, it has some theory in it and has some proofs, and it has, you know, the system itself, and, you know, obviously the problem that we solved, and we demonstrate that we solved the problem, but we also had, you know, some concrete results from the outside world. This is great. So it definitely helps. But it's not enough, right? On its own, the fact that people are using something is not, I mean, even for, like if Facebook does something, like the Facebook thumbs up that goes, right? That's not a systems paper, even though it's used by 1 billion people. So I think that it's the combination of those things. Certainly if you have something that is already being used, it helps enormously.
Okay, and the last question is about internships. So you pointed out about how embedding yourself is really important as a way of sort of understanding what real world problems are. So it's a two-part question. One, is a summer internship enough time to really learn that stuff? And then two, if you're trying to get an internship at a top place like MSR or Facebook Research, it's often helpful to know people at those places first. And so what do you do if you don't? What do you do if your advisor doesn't have those connections?
Okay, so let's see. So first, is a summer internship enough time? I mean, it depends on the company. But different companies are more focused on, even though it's a research internship, they're more focused on like product. If they're working on something, they're probably working on something to solve a real problem. So that is like, they're giving you the problem. So you get to know right away, like, oh, this is a real problem. Like, this is the thing that they want to solve. At a place like Microsoft Research, many people there are focused on trying to do things that will have impact. So I think that the culture of those places is something that you'll learn, and the kind of problems that people are having is something you can pick up. It's not a huge amount of time, right? It can be a very busy time. But on the other hand, Microsoft Research in particular, it's really a research lab that's kind of embedded in a company. And you can then go as a researcher and you can approach people. You have access to mailing lists, and you can meet the people who are working on certain things and just talk to them. And so I had an intern last summer who went and interviewed a number of people. And that was great. We learned a lot. It was tremendously useful. And people are super open to this kind of thing. And that actually happened, by the way, because of something being out on GitHub. So, that we had this thing and somebody actually approached us, and then it was like, hey, how about we go talk to you? So that's that answer. And then the other one is contact. Send me a direct message. That's my suggestion. If your advisor doesn't know anybody at those places, just contact me, and we'll figure out who to put you in touch with.
And actually, we got one last question that I got a special request to ask before we move on to the panel. So if you're working with your advisor to build a real system in verification, and this person says, I find that our research often gets bogged down by implementation. Any advice on how to break out of that rut?
Yeah, so I mean, I think that the question is the implementation like this? When you say bogged down in implementation, right? Like there's lots of ways that could go. If it's implementation because it's like, oh, the system doesn't really work and we have to implement this and implement that to actually make it do the thing. I think that that's important because my experience has been that almost every single system we've ever built, we have discovered that there's something we hadn't thought of. And it wasn't like, oh, blah, 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 Linux, blah, 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 something, right? It was like, oh, shit, here's a conceptual problem we need to overcome. And it emerged during the implementation. And you're like, you discover, oh, this thing is not actually going to scale, or it's not actually going to work unless we solve that problem. That's implementation, but it's also a technical problem. And it's something that, makes the thing, like that solution that you come up with that can solve that problem is much more interesting because you've actually solved the problem. Other implementation details, if it's porting things to certain systems, or I'm not trying to think of thankless things. There are thankless things that are involved in implementing things, but making the thing actually work is, I mean, that to me is not really, it's complicated, but to me, like making something that actually works on real things, that's part of the research, right? That implementation is teaching you something because you're making it connect up with reality. So it depends. Certainly, building systems can be, there are times where you're in a debugging pit for some time. Honing your software engineering abilities is a good thing to do to try to be more effective at that. But I think that if your advisor is saying, hey, this is really important, probably you should trust your advisor. Okay, I'll close with this final thing. My advisor, Catherine, did say, oh, you've done this and you've done this and you've done this. How about we work on Linux kernel level memory management? And I just refused. And I said, I don't think that the research contributions will be worth the implementation hell, having already done some kernel development. And I still think that was the right choice. And so if you can articulate a good reason why you should not implement something, and it's not really on the critical path to some like research thing, and you have other research ideas, say, then you should have that discussion with your advisor. All right, well, thanks, Emery, for the great talk and also for the great feedback and comments and answers to the questions. Let's thank Emery again, and I'll do my sort of solo clapping that will stand in for everybody. Thank you. All right, thanks for
Emery,
the attention and questions.
Yeah. And I hope you'll get a chance to stick around in the Slack and talk to people and answer any other questions that people have. And as Emery did mention, I will reiterate, if you do want an entry point into meeting people at MSR and stuff, feel free, please do ping Emery. He's a great person to know.
Thanks. Bye, everybody.
Thanks, Emery. Okay, so next, as we're getting everybody set up for this next bit, if the various panelists can turn on their videos. So our last part of the PLMW session, or our last part of the last session of PLMW, is our final panel. This panel is called Surviving Graduate School, and it is basically exactly what it says on the tin. Those on this panel are either a long way along in graduate school or have survived graduate school. So we have, they have some experience in the topic that they're going to talk about. But grad school is a stressful time. There's lots of ups and downs. And I think we thought it would be helpful for these various distinguished researchers to tell you a little bit about what that process was like and what they had to go through in grad school and what things they did to survive it. Let me see if I can get this to look correct. While I am doing this, why don't we start with introduction? So I'll go through in the order that people are, that I see people on the Zoom. So Jean, do you want to introduce yourself first?
Sure. Hi, I'm Jean Yang. I am currently the founder and CEO of a company called Akita Software. I did my PhD at MIT between the years of 2008 and 2015. And so I was told that we were supposed to talk about some of the ups and downs we had in grad school. So I'll just describe a few in case you want to ask about them. The initial advisor that I was supposed to join MIT with called me a month before I started and told me he was leaving. And so I ended up working with a different advisor, and then I ended up switching again midway through my first year because Armando Solar Lizama, who ended up being my advisor, joined November of that year. So I can talk all about advisor switches early in the grad career. And then also for the first paper related to my thesis, it was rejected. I think I lost count how many times it was rejected before it was finally accepted. And that was a pretty rough time. So I'm happy to talk about that as well. And there are also many, many ups. I would say grad school was probably the best period of my life so far. Well, besides the current one. But yeah, I'm happy to talk about any of that.
Thanks, Jean. Chandrakana, you want to go next?
Hi, so I'm Chandra, and I am currently just finishing up my 5th year of grad school. So I, actually like Jean, also I'm very happy to talk about, advisor switches during grad school. I did switch my advisor in my first year of grad school, but, to be honest, I think that grad school is an amazing time, and I truly enjoy grad school, and I really like the people I work with and the projects I do. But as most people know, there are ups and downs in grad school. So I'm happy to talk more about each one of them specifically.
Thanks, Chandra. Eva, you want to go next?
Yeah, I'm Eva. I'm currently a tenure track faculty at the Max Planck Institute for Software Systems in Germany, and I did my PhD at EPFL in Switzerland, and I think I finished in 2014, long time ago. I have not switched advisors, though I also didn't take the most easiest of paths because I had a background in my undergrad in half computer science, half mathematical physics, but I never actually took any course in any discrete math. But then I decided to do verification, for which that is actually a prerequisite. So the first 2 years were really, really tough, which meant after the second year, I nearly quit. But then the first paper got in, and then I thought, okay, now I have to stick it through. So if anyone has questions on that, then I'm happy to answer them as well.
Thanks, Eva. And Fred.
Hey, I'm Fred Kjolstad. I'm an assistant professor at Stanford University. So I grew up in northern Norway, and I did my undergrad in Norway. And then I worked for a few years, so I've been worked in industry. And then I moved to the US to do a master's degree at the University of Illinois. And after that, I stuck around in academia for a PhD at MIT, which I finished in January. So I'm pretty new at this professor thing. During grad school, so I spent a while in grad school. The first 2 years were pretty tough, where I just went through 2 years of failures. So that was a little emotionally hard. So that's something I could talk about. But then things started going better, and I sort of found my problem.
Thanks everybody for introducing yourselves and giving a little bit of a flavor of your experience in grad school. Just as a reminder to everybody, we're using the same Slido link that we did for Emery's talk to ask questions of our panelists. If you can also just use the code PLMW4 on Slido to get in. While we're waiting for people to think of questions and formulate some questions, if those of you that did switch advisors in graduate school, I think one of the big stressors that a lot of people just starting out in graduate school have is, how do I choose an advisor? What if I choose the wrong advisor? What if the advisor I choose doesn't quite click with me? Can you talk a little bit about your process of finding advisors? And this goes to everybody as well, but let's start with maybe Gina and Chandra, about your process of finding advisors, figuring out who the right advisor for you is.
Sure, I can go first. So it's really tricky, right? Because everybody has a very specific style of working, and everybody is really famous and really good at doing whatever they work on, but that doesn't necessarily mean that you are going to have a good the way you want to work is going to match with other people's working style. So honestly, I would strongly recommend people to go to visit days and get a feel for the people, all the students who are working, and also get to talk to students in one-on-ones. That I think gives you a good idea of if they're happy, and if they are also what you are, if they're similar to you, and if they are able to work well with a faculty member, then maybe that'll give you a good idea if whether you can do that as well. And also, I think you should, in a few weeks or maybe in a couple of months, you kind of get an idea of where things are going, and maybe if things are working out well or not. So one thing based on my own experience, I would say is that I kind of waited a little bit longer, and in the end, it's actually all fine. But if you know that something isn't working out, then it's better to do a switch sooner, because why waste time, and why just it's hard for everybody, right? If it's not working for you, it's probably not working for your advisor either, right? So it's better to save time and do it sooner. I think also just talk to people more, in the beginning when you start grad school. If that's something that is allowed in your university, and if that's something that you can do, I would strongly encourage talking to more faculty, and just to see what their working style is and so on.
Cool, thanks. I have just a little bit to add to that already great answer, but a lot of people say finding an advisor is like entering into a marriage. I think the flip side of that is that people were very happy with arranged marriages for a long time. You can really make anything work. But that said, when people do have choice, both sides are less invested in making things work at all costs. And so I think there's two dimensions of chemistry that people I think didn't really tell me. I only discovered this after I became junior faculty at Carnegie Mellon, and I was picking students myself. But the way I see it is there's chemistry with the advisor themselves. Is this someone you can sit around and brainstorm with? Is this someone who, when they're giving you feedback, when you're working on things, you're really building off of each other? Is this someone whose working style you can work with? And then there's chemistry with a set of problems that the advisor has expertise in. And I think that sometimes people will over-index on one kind of chemistry and forget about the other. And sometimes that works out. Like I said, anyone can make anything work. But the set of things that I didn't really anticipate was I had a couple of students I tried to work with at various points who just really, we got along really well, but they really didn't have chemistry with the problems that I wanted to work on. And I didn't really have chemistry with the problems that they wanted to work on. And it just doesn't work. Like, I think if both sides are willing to put in a lot more effort, it could, but I think that's a dimension that people don't talk about as much.
Yeah, that's a great perspective. One I, even as somebody who's been an advisor for a long time, maybe don't think about as much as I should. So the current most popular question on Slido is, I think, one that a lot of people struggle with in grad school. How do you handle extended dry patches if you go a year or more without getting a major result, getting a paper in, things like that, especially when you see a lot of people around you doing well? Ava or Fred, do you want to take this one first? Not because you guys have had extended dry patches, but just to sort of load balance.
Ava, you want to start, or should I?
I think my very short answer would be that in general, I found it very difficult to compare myself to others. In general, somehow, if you compare yourself to others, especially everyone combined, is always going to be better than yourself. So that comparison is always just going to make you feel bad. Now, that said, I know this is really hard not to do. But when you catch yourself doing it, I think it is worth it just stopping at that point and just, going back and looking for, in terms of your research, looking for the next small milestone you can reach, rather than, I think these comparisons with others are really bad in general.
Yeah, I agree with all of that. And I don't think you can really do it, because at that point in your life, you may be in your early 20s or mid 20s, and you'll be so different from them that you can't objectively measure, but you can measure yourself against yourself yesterday. And you should be epsilon better than that, because you're mostly similar to that person. And another thing, so going through these dry patches, I think people have a little bit of a wrong measure of what progress is, because they look outside and they look for external things like papers or solved problems. But a lot of the progress in the beginning of grad school, especially when you go through these dry patches, is in yourself. So you're really trying to build yourself up to a person who can solve these problems. And it's kind of hard to measure that. But as long as you feel like you're learning something and you're moving sort of ahead in developing yourself, I think you're making progress.
So that's actually a perfect segue to our next question, which is, what is your opinion on the most effective way to get good? How can you build your PL prowess and strengthen your intuition about work? How can you build that internal sense of progress? I'll throw this one open to anybody.
I can start. I think it goes back to starting with the chemistry with the problem. I think there's, you're probably interested in research in PL for a reason. There's probably things that really catch your fancy. I would start there. Really, go with what you can really find yourself obsessed with, and learn what you can about that. Go deep, develop a taste for what's good, what's bad. When I was in grad school, my friends and I, after talks, used to shut the door and yell about what was good about the talk and what was bad about the talk. And that really helped me develop my taste for this is what I think is good research. This is what I think the bar should be. But yeah, I think also my first couple of years of grad school, I attended every faculty job talk that came through, because I think it's just really important to develop your own internal compass of, this is my taste, this is what I believe, but at the same time calibrate, this is what other people deem good, this is how other people are describing things. And I think just really absorb as much as you can in the beginning. And I think, like I said, it's if you really actually love something, you're able to absorb much more, and you'll find that you have like an internal strong view of, this is good, this is bad. Sometimes it takes a while, maybe a few years, to really uncover. And so try to get a feel for that in yourself.
Yeah, I think you just sort of have to do a lot of things. And there's this period where your taste is better than what you can actually do. At least I found that. And you do all these things and you see yourself that they're not so good, but you still have to do them because otherwise you're not making progress. And I think one thing to be careful there is until you start producing things that are up to your own taste, you shouldn't start to write so many papers, because then you spend all this time polishing things that you may not yourself not like. And then you sort of prevent yourself from developing into someone who can do the stuff that you like.
So I could add one experience to this. So for me, I think I learned the most by doing research projects. So, you know, looking back, my first big research project in grad school was, you know, me building an entire CAD compiler from scratch in OCaml. And that was the biggest project I'd ever done. And, you know, it just took forever, but I learned a ton from just doing that project. And the other thing is that I also would strongly encourage people to ask, you know, senior students or, you know, whoever, like any mentor you have, like just ask questions. Like if you don't understand something, like don't hesitate to ask, because, you know, I have hesitated to ask questions, you know, early on in grad school, and I realized that that wasn't really a good idea. So if you ever have a question, don't be shy and ask, and then you'll learn a lot more.
So perhaps I can add one more thing. One thing that I found very difficult and that I think is very useful is to consciously step out of your comfort zone. So for me, giving talks and attending conferences, just generally talking to people at the very beginning of my PhD was really hard. Now I had an advisor that more or less forced me to do it. And now I'm very grateful, because this is also part of research. You have to talk to people, you have to talk about your own research. But initially it takes a really big step, and consciously looking for these opportunities to step out of your comfort zone, I think that also helps you quite a lot.
So a question for everybody that wants to answer, which I think is something that's on a lot of people's minds. Have any of you experienced imposter syndrome? And if so, how did you deal with it? And actually, I don't know that I have the best definition for imposter syndrome. So if somebody has a good definition for imposter syndrome they would like to lead with, that would also be, I think, helpful for a lot of people. I can give my definition of imposter syndrome, which is very much that feeling of like, I don't belong here. Like I'm not smart enough to do this. Like people are going to find out that I don't belong here. People are going to find out that I'm not good enough to be here. I think it's a very common feeling for a lot of people when they get to grad school, and really whenever they start anything new, or even later on in that process. Have any of you guys had to struggle with that? Any thoughts about how you can cope?
I can start if that's okay. So I definitely understand this feeling, and that's because my undergraduate was not in computer science. And, you know, I decided to do a master's in computer science. And so I went to EPFL, and which is where I met Ava for the first time. And, you know, I started working on a research problem with a Turing Award winner. So I worked with Joseph Sifakis, who had shared the Turing Award for model checking. And, you know, it was just unbelievable, because I had no idea what I was going to do. And, you know, I started working on a project with you know, some senior grad students, and for the, you know, it was just very scary. And you know, every time someone would say a term, I would just not know what it meant, and then I would have to like quickly search for it, or like, you know, like you know, ask somebody secretly, and like it was just very stressful in the beginning. But like Ava said, and also, you know, as I was saying previously, like I think the best way to overcome, if you really don't know something, that, you know, the best way to overcome is to ask people who know it, right? And that can be very uncomfortable to do that. But the sooner you do it, the sooner you'll know it. So you know, the sooner you'll overcome that anxiety. You know, even in grad school, like, you know, I'm sure most people, you know, go through imposter syndrome. And I think the best thing that happens that lets you overcome it is you have a paper or two, and then you kind of, you know, give a talk or two here and there, and then you kind of get the confidence that you need, and it helps overcome the imposter syndrome.
Yeah, I think that getting the confidence is great advice. I just have a couple of things to add. So when I was an undergrad, I took this grad seminar with one of my professors and I never spoke up. And one day she took me aside and she said, "Hey, you never talk in my class. Why is that?" And I said, "Well, I'm sure other people just have better things to say." And then she said, "Have you heard of imposter syndrome?" And she taught me all about it. And so that was the beginning of my realization that, you know, maybe my feeling that other people have a better thing to say is not actually reality. And I had another professor who said, well, she told me it was a gendered thing. She said, if you look at the guys in the class, they're not saying more correct answers, they're just saying more. And she kind of very rationally broke it down for me that not talking was actually holding me back. And so I think after that, I just came to see it as something to calibrate against. So I don't know if any of you guys are runners, but when you're running, there's just after some number of miles, it's just painful and you just have to ignore the pain and keep going. So I kind of see it as that. So if you ever have this feeling like, oh, I'm not good enough, or I don't know what I'm doing, that's just a feeling. And then you put it aside and you ignore it. And then you kind of just keep going, if that makes sense. And so I think for, especially since the beginning of grad school, after I got the first few proof points that, you know, I deserve to be there and I know how to do research and all of those things, I think that it's not that the feeling goes away. It's that you learn it's a normal feeling to have, and it's not like an alert that you really need to pay attention to. So something I often think about is, I don't know if you guys know about this guy, Kobayashi, who's like the world champion hot dog eater. But he has these great interviews about how he eats more hot dogs than anyone else. But he's like, you know, after some point, it's just like this feeling of disgust and like it's awful. But if you can push through it, then you have euphoria. And I feel like for imposter syndrome, that's kind of like for any kind of confidence thing, that's just what it is. Like, you know, there's always these feelings of like doubt or uncertainty. But if you can push through it, then you have euphoria.
Yeah, I think that's very good. That's really good. For me, the way I sort of addressed this was a little different because I was coming from rural Norway and then suddenly I was at MIT and I just accepted that everyone else were better. And I figured it doesn't really matter if they're going to let me be here. I'm going to be here and I'm going to learn as much as I can from these people. And maybe I'll absorb some of it at some point.
So I think Richard Feynman, the famous physicist, also wrote something like this in one of his biographies when I think he got a professor position at Stanford, where he said, well, that's the other people's problem. They got me the position, now I'm just going to enjoy it. And I think just reminding yourself of this helps. The other thing I have heard on, I think, several occasions was the saying, fake it till you make it. So you just pretend you're good, just as good as everyone else seems to be, and then gradually the feeling will never go away, but I think it does become a bit better and easier to deal with.
Yeah, I might be a little cautious about faking it. Ralph Johnson at UIUC once told me that if you want to be good, you should reveal your faults, and because then you can correct them. But there might be a balance to be struck.
No, I meant faking being confident. Not so much faking what you're, just saying some fake things, but pretending you're as confident as everyone else appears to be, even if you're not quite that.
Then I agree. Sure.
So I have a handful of questions that are sort of like quick fire questions, one to each to individual people, and then there's a couple more broader questions. So these are not necessarily the highest rated questions, but they're sort of individual questions that people had. So there's a question for Fred about what difficulty you faced coming from industry and what advice would you give to your younger self in dealing with that?
So I worked for industry in Norway. I worked for ARM, the company that make microprocessors on their graphics processors, which we made in Norway. And I think the main issue, there's two challenges coming from industry, two main ones, and those are just about getting out of industry. One is if you spend all the money you make, it's very hard to downscale your lifestyle. So my solution to that was I didn't know that they paid for school in the US. So I just tried to save up everything I thought I would have to pay. So I didn't spend any of the money I was making. And the other issue is that there's a different value system in industry versus academia, where a lot of the things in academia are sort of seen as, sometimes seen as useless in industry. And I think that's a little short-sighted, because if you look back 20 years, industry people would certainly agree that the things that were developed then were useful. So presumably that will hold in 20 years too. But getting out of that value system and sort of embracing the academic value system, which is more about building knowledge than actually building engineering tools. Although, I mean, you can do both in academia, as Emery just talked about. Yeah, I think these are some of the challenges sort of moving to academia. But I think the benefit of coming from industry is that you're going to be a stronger engineer than you would otherwise have been. And that can be useful, but you have to back out of that, because you're not in academia to be an engineer, you're there to think. But when you actually have to do some engineering, that can come in very handy.
Thanks. A question that I think, Ava, you might be well positioned to answer, given your story about how you sort of switched topics a little bit when you moved into research. How do you deal with missing some basic prerequisite topics when you're trying to get into your own research field?
Well, you have to read probably a lot of papers, ask a lot of questions. Possibly one way of getting this extra knowledge is to be a TA for a class. I felt each time I was a TA, that's the time I actually learned the material. Whether this was in my undergrad or whether this was now that I'm actually a faculty. But always teaching a class, be it just a graduate seminar, that really forces you to understand the material properly. But yeah, I think there's really, you just have to sit down and just learn. That said, sometimes I feel like it's best to just start a project and learn on the go rather than first spend months trying to just read books. So it's mostly you want to have some motivation for why you're reading something. Otherwise, you know, you're just gonna read it and forget it tomorrow.
Thanks, Ava. Yeah, I totally agree about, you know, there's definitely something to be said about just learn by doing. Gene, a question that sort of stemmed from something that Mike talked about in his talk this morning was that it turns out you're the one that started PL Lunch and PL Offsite and did a lot of the community building at MIT. Can you speak a little bit more to that and what that was like and what, you know, the benefits and maybe, yeah, what that process was like?
Yeah, sure, absolutely. I think I'm a pretty community-oriented person, and so if there isn't a community already existing, then I try to facilitate it. And so I think for PL at MIT, it was in a really interesting transitional point when I started. So I started my PhD in 2008. That was when Mike Ernst, who's in at UW now in software engineering, had just left. I was supposed to work with Mike Ernst and Saman Amirasinghe, who was Fred's advisor. And, you know, I lost half of my co-advisors right before I started. Daniel Jackson was there, Martin Reinhard was there, and then Charles Leiserson and Arvin and some other professors were doing work around PL. And they, you know, they would attend PLDI and POPL, but they weren't considered PL. And MIT definitely didn't have a PL group identity. I had really liked MIT because of its very systems focus. And so that was why I went there, despite the lack of core PL identity. But I did feel like there was a lot going on around PL, but nobody talked to each other. So I actually talked with Saman and he said, well, why don't we do this offsite? And I think Saman saw that I liked building communities, so he would just whisper things to me and I would do them. So he's like, well, you know, if you got all the professors together and made everyone chip in $100 per person at this location, then we could have an offsite. And I was like, oh, good idea, Saman. And I think no one really knew that Saman was the puppeteer, because I feel like, you know, a first-year PhD student is not savvy enough to pull this thing off on their own. But he's like, all right, so here's the strategy. So we would have like these weekly meetings where he'd be like, here's who you approach. This is the order I do things. This is, you know, where the money will come from. These are the words you say to unlock that money. And you know, so I really think it was very much Saman's like a deep collaboration with Saman. And then the first time the offsite happened, it was really the first time we got all of the PL researchers at MIT in the room at the same time. And it was a revelation. People were like, oh my God, I didn't even realize other people were working on the same thing. How many years has it been since I talked to them? And for me, I had gone to visit day. So that, you know, the reason that all those people are around was why I came to MIT. So it was also an interesting moment for me because I was like, oh, they could all be talking to each other. So I think after that, the professors all had a meeting where they were like, we're going to do better and talk to each other more. And then again, someone said, why don't you do this PL lunch thing? So I think it was really, it was mostly the professors were pretty siloed, and then Saman had this idea that things should be less so, and he knew that I would do it if he suggested it to me. So then I did it. But I think this is related to a piece of advice I have about life. Like, you should always just do the things that people more experienced and smarter than you tell you to do. Most of the time, because it's usually like a better idea and the execution is going to be better than if you did it yourself. So I still very much follow this. I think sometimes like I have my own idea and I'm like, yeah, I'm pretty sure this is going to be a great idea. But in the absence of that, I usually just try to do things that people who are better at life suggest to me.
As an aside, not directly related to PLMW, was Zoom Bachelor your own idea or one that somebody suggested?
Yeah, that was actually one of my own ideas. I recognize that as, you know, it can go in the category of ideas other people give me.
Okay, so a broader question for everybody, but I want to start with Chandra kind of. Do you have any cautionary tales of things to look out for and avoid during grad school?
So I think one thing, you know, I did in the beginning of grad school, which I would probably not do if I started grad school now, is try to build something, you know, sooner than later. Like, you know, it may not be the final thing. You may have to just throw it away. You shouldn't just start building anything right away, but like after, you know, a few, you know, iterations of reading papers and like, you know, talking to advisors and stuff, I think that really gives you a very good idea of whether whatever it is that you're thinking of doing is going to work out or not, and whether you actually enjoy doing that or not, right? So those are things that, you know, the sooner you get your hands dirty by doing something, the sooner you actually know the answers to. Yeah.
Cool. Yeah, my related cautionary tale has to do with my last piece of advice, which is, you know, just listen to people who are more experienced. So I think in grad school, a lot of the other students and I felt like we had to forge our own identities. And, you know, I feel like the middle of grad school is just one long teenage rebellion where people are like, my advisor told me this, but I'm going to do it this other way. And then, you know, like, I think learning when your own judgment is better than your advisor's is definitely a journey that every grad student goes on. But I think sometimes for some things, if your advisor is like, just trust me, I know better than you, you should just listen to them. Alternately, I also spent a year working on something that my advisor kind of offhand suggested, but it was not that interesting. And I knew it was not that interesting the whole time. I should have spoken up earlier. But I think, you know, like having a dialogue with your advisor so you can even get a sense of what they're confident about and what you should listen to them on is really, really important, I think. And when I was on the other side of things, like I really saw that, you know, I realized, okay, here are some things that I really just don't know, you know, they shouldn't listen to me on, but there are some things that I know there's a better way to do things and people are not listening. And it is not only frustrating, but it's just taking time. It's taking time that the student could be developing in other ways.
I would say one more thing is be careful to pick an advisor who sees it as a platonic business relationship where you're going to do research together, because it is an apprenticeship relationship. And the advisor should be invested not just in the research you do, but in developing you. And that's very important. And I think most advisors would be. It's something to keep an eye on.
Perhaps I'll just add one more thing that took me years to realize is that I actually had to ask for feedback it turned out that for some people is when they don't tell you things or don't criticize you, it means you're doing fine. But this is hard to tell. And it just took me a really long time until I mustered up the courage to actually just actively ask for it. And I should have really done that much earlier.
I have one more
Okay.
thing to add.
Yeah.
Okay. So I think another thing to look out for, this I'm speaking as a student, not as a professor, but it's very easy to take up a lot of responsibility in grad school, and a lot of people do that kind of thing. Like there's so many committees and so many volunteers required for this and that here and there, and each of those things take a lot of time. So one thing that my advisor often tells me is do one extra thing while you're doing your projects or research project, right? So that I can manage, but if there's more than that, it usually takes up a toll on research.
Yeah, that actually goes quite nicely into another question, which is how do folks manage time in grad school, especially before deadlines, but in general, how do you manage your time in grad school? That it's to embellish that a little bit, right? Grad school, all of a sudden you have a lot more freedom compared to undergrad. There's fewer things that are really regimenting your time. What kinds of strategies did you use?
So when I was in grad school, I was pretty extreme with my time management. I worked between 8 and 9 a.m. to 5 or 6 p.m. And my biggest goal was on weekdays mostly. My biggest goal was to avoid burnout. So I on purpose tried to prevent myself from working too many evenings and weekends. But that was at the cost of pretty much focusing very intensely during the day. Like if someone tried to talk to me during the day, for many years, I just wouldn't talk to them. So that is something that I've since relaxed that, because I was like, this is no way to live. But then before deadlines, I would work all the time. And so for the month or two before deadlines, I pretty much just worked all the time. I don't think that was a good idea, because then I would be burned out for the month or two after deadlines. But I do think that like keeping very regular regimented hours, staying focused during them, and forcing myself to take time away for like those parts, my attention and my focus were really good. But yeah, the working all the time part around deadlines was, I would say, like wrecked my focus for a while after.
I think it was hardest to manage my time when there wasn't a deadline, and it was sort of just open time. Around deadlines, you just work whenever you can, and maybe it's not the best idea, but sometimes you do it. In the beginning, I had no discipline at all. I just worked through nights and all sorts of things. Also when there were no deadline, but towards the end, I really adopted something much more stringent. I get up at this time. The first 2 hours are for thinking, because that's when I can think in the day, and then I can do other things, and then meetings in the afternoon, and then some time away from work after that. So I became much more disciplined.
I actually have tried a bunch of different ways of working. So early on in grad school, I was kind of like what Fred said. Like I would just stay very late in the lab, and like 3 a.m., 4 a.m. and like I had a friend who would give me a ride home and stuff. So I just like had no discipline at all. And then towards after the first couple of years, I kind of started to be a little bit more disciplined. Like during the day, I try not to look at email or Slack unless there is a message specifically for me. But those things actually take up a lot of time. Like because it's very tempting to like check Slack all the time and check email all the time. Maybe there's something interesting somewhere. But those I recommend not doing those things, at least for 4 or 5 hours. During the day when you're just thinking about research problems. I think, yeah, for deadlines, like Jean said, like I just work all the time during deadlines. There's everything falls apart, which is also not very good. But one thing that I always do, even during deadlines, maybe not the week of the deadline, but up until that, I don't stop going for runs, because one of the things that I really, really enjoy is, going out and doing some exercise, and running has been very, very helpful for that. So yeah.
Yeah, I can only second that. what has been said so far. So I also try to have, well, I tried to have, and also now just have a fixed schedule. I work from this to this hour. And actually, after the biggest deadline during my grad school experience, I came back to the lab the most tanned that people have ever seen me, because I literally went for a run outside every single day just to, apart from that, I just worked, but I always took the time to at least do something, some exercise outside.
So another question that folks have, that I think a lot of people have uploaded, and I don't know if anybody has the answer yes to this question, but I think it's something that's worth reflecting on. Have you ever considered quitting your PhD? Did you ever consider quitting your PhD?
Oh, I consider quitting all the time, so I'll take this question. I think at one point my friends had an intervention and would leave fortune cookies on my desk. Like, it doesn't take guts to quit, because they're trying to like intimidate me out of quitting. So I think early on in my PhD, a bunch of my friends actually did drop out to start their own companies, and I had a lot of FOMO, because it seemed like their lives were really glamorous, and I felt like I should also experience such glamour. I think also when you're in computer science, the opportunity cost is just really big. You could be making a lot more money in industry. You could, there are interesting things you can do at a lot of companies without necessarily having a PhD. Just being a PhD dropout in programming languages gives you access to a lot of the same things. And so I think for me, it was pretty much a constant existential question. I think that, like, in retrospect, I feel like if I had just like calibrated that away and been like, this is a feeling that will be constant in my life, this is just the kind of person I am, I could have just like had a happier and more productive existence, because that, like, half hour every week that I spent thinking about this, I could have just like been doing other like actually like fulfilling things with my life. And so yeah, I think it's not the logical choice usually to decide to stay in your PhD. I think you really have to have some sort of devotion to the area. I think you have to, like, everyone needs to have some like pretty strong reason to like stick with it. I think for me, ultimately, it was, I really liked what I was doing. I feel like most of my learning and growth through my PhD really came from wrapping things up at the end. And I kind of had a sense that that was the case, that if I just walked away in the middle, they're like not tying a bow on things was really depriving myself of a lot of the growth that I was building up. And so so for me, that was a big part of why, like, at the time I decided not to just quit. I think my reasons for quitting are probably also different from other people's reasons. So other people can also talk.
I considered quitting 2 years in. I decided I was going to give it one more year, and if I didn't make any traction, or at least what I felt was traction in terms of papers or something like that, I would quit. But then things started easing up, and I don't know if I would have quit or not, but it was definitely on my mind. Another thing is, like, for me, I was a little older when I started my PhD, and I felt I would be so old when I'm done with my PhD, and that was really concerning to me. And then I realized that I would be that much older after that much time anyway, and that was a revelation to me, although it's very obvious.
Yeah, I also was very close to quitting 2 years into my PhD. I had more or less an offer, well, not in writing, but I was told I could have a pretty well-paying job in industry. But that was exactly the time when my first paper got accepted, and then it was partially a bit of pride where I said, okay, so now the first time it worked, I know now I can just do it another time and I can get another paper published. But I also, just as Jean said, I really liked what I was doing. I chose to do a PhD because I really wanted to learn about the topic of program verification, and I knew that there wasn't all that many places in the industry, at least at the time when I started, where I could really do this. And this was what really kept me going.
There's no place in the industry where they would just pay you to sit for years and try to develop yourself and think about things. Unless you're already famous, then maybe.
By the way, just to make clear that there's not, or rather to give more credence to the fact that I think a lot of people think about quitting their PhD. I also thought about quitting my PhD part of the way through. I think it's an extremely common thing to happen. So if that's happening to you as a graduate student, you're not alone. This is very common. Talk to your friends, talk to your advisor, talk to other mentors you have, and also, you can be shamed out of quitting your PhD maybe, and you can feel a lot of pressure either to quit or not to quit. I don't think that there's a right or wrong answer. It's sort of a general answer. You talk to your support network and think about what the right move is.
So I honestly didn't actively think of quitting my PhD, but when after my first year, I was looking for a new advisor. I was actually very stressed because I thought maybe I won't find an advisor and maybe I'll have to drop out. And I'm an international student, so the logistics of that were like horrifying. I was like, I don't even know how this is gonna be. Like, what am I gonna do? But things worked out in the end, so I didn't end up having to think too much about it.
You can always quit next year. So if you feel like you really shouldn't, but really it's hard to keep going, you can go on for a little bit longer and see if you can keep it up.
Yeah, like most of the industry jobs are still there 1 year from now. But if you quit your PhD, it's really hard to come back.
Okay, so here's a question that I'm going to read out exactly because I think I want to make sure I say it properly. So you may not have an answer, but I am trans, early in my PhD, and will probably change my name soonish. How should I think about publishing?
I think if this person knows what they want to change their name to, publishing under the new name makes a lot of sense.
And I think a lot of people find papers to your webpage, and so I don't think it's going to be a big issue with having different names on different papers. I think that'll be sort of managed through your webpage.
Yeah, I think DBLP is pretty good about this. I know a person who didn't change genders, but changed their name like 5 times. And DBLP just put all their names on one page.
Yeah, it's a. I think it's a question that comes up in a lot of different contexts. Not obviously, there's this one. There's questions about people changing their names when they get married. Issues like that as well. But I think it is getting easier to manage that sort of stuff because of systems like ORCID, DBLP, stuff like that. We'll post a couple of resources about name changes in the Slack. Okay, so here's a fun one. If there was one thing you could change about your grad school experience, what would it be?
I think for me, just spending less time angsting. Like I feel like, I don't know, I just had a lot of angst early in my grad career. I'd be like, should I even be in grad school? What should I work on? I'm working on this. Should I keep working on this? And what I tell people now is all the time you spent angsting, if you just spent doing the thing, you would be done. And then you wouldn't have to worry about should you be doing it anymore. And so I feel like I could have saved myself a lot of time if I had just like gone back in time and given myself that advice over and over again.
Yeah, I think I would have also said just not worry so much. I'm still fighting with that. I still worry. Now I have a husband that's telling me pretty much every day, just don't worry, it's gonna be fine. But if I could have just done it myself back then, I think it would have just made a lot. I don't think it in the end would have made such a huge difference on what I had really accomplished. It would have just been a lot more fun.
Chandra, Fred, you guys are pretty happy with how things worked out in grad school?
I mean, it wasn't always comfortable, but I think some of the discomfort was necessary for growth. But I think not worrying so much, which Jean and Ava said this, I think that's great.
I think it's similar to what everybody else has said here. I wish I was more, willing to do things that I wasn't comfortable doing in the beginning of grad school. Like, I'm still a grad student, so I don't want to say too much before I get my degree. But there were times in the beginning of grad school where, like I said, I was always hesitant to hang out with people and ask them things that I didn't know, or like be in the lab and do like pair programming and things like that. And I think that in the end, like, now I'm more comfortable doing those things. And I think they are better, actually. Like, they make me better. I learn more things like that. And I just wish I, was less, conscious about these things and more like braver from the beginning.
Okay, here's another question for everybody. Are you more productive when focusing on a single project or when working on multiple projects?
So I can say something here. So I usually am better at working on one project at a time, but I think I'm more productive and have more things going on. So for example, the quarters where I have been TAing, taking a class, and had a paper deadline, I think those quarters went really well for me because like there was no time to waste, right? Like you just have to do either, there was either this work or the other work or the other work. So there was just no time to waste. And I somehow got more done in those quarters. But I personally feel like if there are two projects that I'm leading, both of which I'm leading, I find it hard to juggle the time between them because, it's very easy to just spend all your time on one project and not give enough time to the other one. So it doesn't quite work out that way very well for me.
Yeah, I agree with all of that. I found also it's very hard when you're working on something very thought intensive, like writing a thesis or sort of really when you're starting to develop the ideas. It's hard to work more than about 3 or 4 hours on that, and then you're sort of done for the day. And then the question is, what do you do with the rest of your day? And I found this useful to go to the office, talk to people, and just sort of do this. Less immediately important things, but the kind of things you can do without your full attention. Yeah. Or just take the day off, the rest of the day off. I think a lot of the theory people do that.
Yeah, no, I agree that like for the really thinking intensive stuff, I do best when I focus on one thing at a time, but then you have to fill the rest of your day somehow. And for me, it was always having one major thing that I spent a lot of thought on, and then one really easy thing that I could always make progress on. That was kind of a hobby. So like organizing the PL stuff was part of that. I also started Graduate Women at MIT when I was there. And that stuff is just like, everyone knows how to organize a group. You can experiment with how to make it better and worse, but it's not rocket science. And so I always do best when I have a project like that it's kind of like guaranteed progress. I know how to do it. I don't have to think too hard. It's just about executing. And for me, that kind of stuff also always got me through the rough periods, because I'm just emotionally, if there's something that's really easy and you always have a consistent sense of progress, is just very good to not lose momentum.
Okay, so I think we have time for one last question before we have to wrap up our panel. There's quite a few more questions on Slido that we haven't had time to get to that I think could lead to some good discussion. So hopefully, if you guys can stick around on Slack or in Disco afterwards, that would be, I think everybody would really enjoy hearing more from you guys. But maybe sort of as an opportunity to provide one piece of wisdom to people that are just starting their grad school career, or maybe even just thinking about going to grad school right now. How can you position yourself for success at the beginning of, or even before starting grad school? Let's go around. Jean, you want to go first?
Sure. Yeah, I think that something I'm never figured out how to describe until I recently was working in a group with this executive coach, where she talked about the narratives you have around things. And so, if someone says, oh, meetings are always really, really tense or something, she would say, well, why do you think that? Why is that the narrative you have about that? And I think that a lot of people have this narrative that grad school is supposed to be really hard or miserable, or it's going to burn them out, and it's something that they have to fight against. And I think for me, pretty early on, I realized that that I was in control of that narrative. And if I wanted grad school to be a really good time and just really fulfilling, that was on me. And I think that really changed my experience of grad school. And so I had a lot of friends who they'd be like, Jean, you're having too much fun. Do you even work? You're so happy. But, you know, I was just like, look, this is your narrative. Grad school doesn't have to be miserable and too intense to be grad school. And I think that it's not like the work materially changes. You can still work hard and learn a lot and be uncomfortable, but have like shape the narrative that this is a really fulfilling and wonderful time for you.
Just going clockwise or counterclockwise. Chandra, you want to go next?
Sure. So actually, one thing that Mike said in his talk earlier today was very helpful, and I very strongly agree with it, and I think it's very helpful, is that don't get too worried if you have to learn some new skills. This is for early on in grad school, right? Or before grad school even. Like, it's very likely that you're probably going to, work on something where you don't necessarily have all the skills and you'll have to learn it. And that's fine. Like, that's what you're here to do. So it probably will take a year or two before you get your first big publication, but that happens. And I think it's not that big of a deal. And the other thing is, this is something that I've learned from my advisor. He always says, like, the most important thing is to be persistent. Like, just keep doing the thing that you're doing. Don't worry too much. It's very easy to get distracted by other people's papers and successes and all those things and compare with them. But if you just keep doing the thing that you're supposed to do, things will hopefully work out.
Fred?
Yeah, so one danger is to become disillusioned and sort of cynical and feel like everything is a sham. And I think that happens when you sacrifice your values. So don't do that ever. So for instance, there's one narrative that people often get into, which is academia only treasures papers. So I have to write all these papers I don't care about just to sort of play the game. And I don't think it's true. And even if it was true, I would not go down that path unless you really cherish those papers yourself.
Ava, any parting thoughts?
I don't think I have anything to add. I think what Jane said is really spot on. I think it's really, it's not so much what you know, what you've learned before, it's what you're going to learn during the PhD. That is really, I don't think you can really set yourself up by learning before.
All right. And with that, we have come to the end of our panel, and we have actually come to the end of PLMW. So thank you, everybody, for sticking with us for 2 days of virtual PLMW and bearing with us with the various technical difficulties and things as we got this all up and running. I want to especially thank the following sets of people. I want to thank all of our panelists and speakers for participating. So let's give a round of applause first to Jean, Chandra, Fred, and Ava. Or I'll give a round of applause, and you can imagine that this is reflected by everybody else. But let's also thank the rest of our panelists and speakers from the rest of PLMW. I want to thank our student volunteers who helped getting everything up and running and making sure things were running smoothly on the stream and on Slack. I want to thank I think 150 odd people that were in the Slack and for all of the great discussions and jokes and stuff that were going on during the various sessions. I want to thank all the people that watched us online. Thank you very much for joining us. I hope this was helpful to you. The Slack is going to be running for the rest of PLDI. The videos will be available for the rest of PLDI, if not longer. We'll all be around. So please keep asking questions, keep chatting. We want to build this community and this network of people to support each other in PL. PLMW is a big part of how we do it. And we hope that you'll stick with us. So thank you, everybody. And I think that we'll probably have disco going afterwards. So feel free to join us there if you want to keep chatting.
Thanks so much for organizing.
Thanks.
Yeah, thank you.